Yeah, can you hear me now?
Yes, sir. Sir, please start.
Okay,
Thank
perfect.
you.
Thank you so much for the introduction, and I sincere apologies for not being able to be present over there, and also, for all the audio difficulties. I'm going to try and share my screen just so that I can. Okay. Let me know when my screen is visible,
It's visible,
and
sir. It's visible.
uh, okay, perfect. Great. So I'll talk today about physiology guided AI for outcomes prediction in medical education. And I'm an associate professor now with the Department of Medicine at Pulmonary Critical Care and Sleep Medicine and the Department of AI and Human Health at Icahn School of Medicine at Mount Sinai. My team is part of this sleep and circadian analysis group that I lead at Mount Sinai. We are a four-bed research lab that sort of undertakes physiology-based sleep studies and some respiratory experiments as well. We are located in Midtown Manhattan, and these are some of the example bedrooms that we have. Um, we are affiliated with an 11-bed clinical sleep lab that is at Mount Sinai, and this clinical sleep lab evaluates clinical sleep apnea patients and those with comorbid respiratory COPD, asthma, and other disorders. And as was mentioned, I have three key research areas. First of them is to develop physiology-guided AI models for predicting outcomes in sleep medicine. Second is to use next generation AI ML techniques to build educational tools in sleep medicine. And third is to identify mechanisms underlying consequences of sleep disorders. Today, I'll be talking mostly about the first two of them. And so let me take you through them. So, the disease that I predominantly work with is sleep apnea, and it's a common chronic condition that is characterized by apneas and hypopneas, and it's essentially an upper airway obstruction sort of disorder. Apnea is when there's complete cessation of airflow, and hypopnea when there is reduction in breathing due to partial blockage of the upper airway. The common immediate consequences as a result of apneas and then sudden wake up and arousals are that sleep is fragmented throughout the night, and it is also associated with intermittent hypoxemia throughout the night. And these are the two main characteristics of sleep apnea as a disease. The common way we sort of diagnose sleep apnea is by routine sleep studies or what's called a polysomnography, and it's trying to look at different end organs and their activity throughout the night. And so, in a snippet example shown over here, you can see that the region marked by the black arrows is when the airflow was completely sort of stopped or blocked, and it was associated with increased effort. So there's an effort to actually breathe, but there is no airflow. And that's the hallmark characteristics of obstructive sleep apnea. It's also associated with oxygen desaturation over here. And so every time there's an apnea, hypopnea, there's this oxygen desaturation phenomenon that goes hand in hand with it with a certain sort of delay. The diagnosis main metric clinically, sort of globally, that has been used is the apnea hypopnea index. And it's essentially, as I said, consists of characterizing apneas, hypopneas, which is partial obstruction that results in either oxygen desaturation or EEG measured arousal. And so AHI is nothing but the sum of those apneas, hypopneas divided by total sleep time. And so if a patient has HI greater than 5, then it is considered that they have sleep apnea or at least some form of sleep apnea. And if they have HI greater than 30, then it's sort of deemed that they have severe sleep apnea and should get on immediate treatment. In terms of the prevalence, recent estimate was put at about 1 billion globally, people affected with sleep apnea. And in India alone, it's sort of more than 100 million based on a recent study that was done. It's associated with incident cardiovascular, cerebrovascular disease, Our work also showed that it's associated with neurocognitive impairment. And one of the common complaints is daytime sleep, asleep throughout the day, be it as a passenger in a car or after lunch and so on. And so those are some of the common complaints that sleep apnea patients exhibit. And in one of the seminal studies that was done in about 1990s to 2000s, looking at a large cohort of about 6,000 individuals followed for 10 to 11 years, it was noticed that those who had severe sleep apnea, shown by the red line over here, had a highest likelihood of incident cardiovascular disease leading to a fatal event. And if left untreated, sleep apnea leads to other disastrous consequences. And it is sort of one of the main, I would say, complaints in terms of sleep medicine that patients sort of report. So you would think that it's, pretty simple. You look at apneas, hypopneas, count them throughout the night, and it should tell you if they are sleepy throughout the day, it's because of their sleep apnea, and you can correlate the two. And if they get treated and if the AHI comes down, then sleepiness should be resolved. But that is not the case at all. So in this recent data by a Pittsburgh sleep clinic, and this is true for most of the sleep clinics that I have observed at, the relationship between the severity of the disease, which is on the x-axis, apnea-hypopnea index, and the severity of the outcome, which is on the y-axis, that's the Epworth sleepiness scale, is although present, but very weak. So you could have individuals or two individuals who have similar severity of sleep apnea, but have very different severity of sleepiness. And so in the field, people have been trying to understand what are the physiological characteristics that can tell us why people with same severity of sleep apnea have different, severity of outcomes. And in doing so, what people have started, looking at is closely at the apnea hypopnea index. So AHI-4 is one of the commonly used metrics, and it's apnea or hypopneas associated with more than 4% desaturation. And then people started complaining that 4% is maybe too high. They should also look at 3%. So the Academy of Sleep Medicine also proposed using a different definition, which was using 3% desaturation and or arousal. And based on this sort of study that was done in 2015, depending on the metric you use, AHI could vary from as low as 11 to as high as 25. And so what definition should you be using? And if you use, what happens to sort of the outcome? And why is there such a big variation in them? So increasingly, people started realizing that AHI is a very simple metric and may be useful in certain cases, but is definitely not useful when it comes to predicting outcomes. So over the years, several investigators started looking at different metrics. So hypoxic burden was one of the metrics, trying to look at the desaturation profile. Cardiopulmonary coupling using another wearable sleep device was proposed as a novel metric. Some have looked at the event duration of apnea hypopnea and shown that it predicts mortality in men and women in that large study. Arousal intensity, which was time spent in arousal during sleep, was also looked at one of the other metrics. Odds ratio product, again, similar to the arousal intensity, was an EEG metric. Based on the photoplethysmography or PPG signal, looking at the pulse rate response was another metric. Pulse wave amplitude drops, flow limitation in the airflow, and so on and so forth. And so what happened throughout the years is people started putting out all of these different metrics, and for clinicians and researchers alike, it was very confusing. So which metric should we be using if not AHI, and what is the benefit of one versus the other, and in what cases should you be looking at one metric and not the other, and so on. And so my objective today is to sort of, give you a more harmonized framework and walk you through how inadvertently all of these studies had looked at different aspects of the physiology and have inadvertently provided some of the components that could then be fed into an AI or machine learning model to better predict the outcome. So we'll take a closer look at the AHI and use the constituents or the components of AHI to redefine the presence of abnormal breathing and redefine the classification of the severity. So we will propose not the usual, mild, moderate, severe categories, but somewhat of a different staging classification. And in the sort of whole pursuit, go beyond the AHI. And so that's sort of the main motto of all of this work is to go beyond the AHI, look at the disease, and try and develop better AI or ML related metrics. In going beyond the AHI, we'll touch upon how we are using multimodal AI models, and is there a role for generative AI models, such as the recent large language models and so on. And so hopefully by the end of the talk, what seems to right now to you as a more chaotic, framework and the disease and outcomes and so on, by the end of the talk, hopefully it'll all come together and it'll start to make sense and you can see a path forward on how physiology can inform these ML models and be used to better predict outcomes. So taking a closer look at the AHI, it consists of three components. As I said, it's apneas and hypopneas. Hypopneas that are associated with arousal or desaturation. So there are three components: ventilatory, hypoxic, and arousal. And as we know from several studies that you could have two individuals who are at opposite ends of the spectrum, either in the ventilatory or hypoxic domain. So someone who has a very deep desaturation, so saturation goes from 95 to maybe down to 85, whereas another person goes from 95 to 90, but both have the same frequency. They will have the same AHI, but not necessarily the same disease in a way. And so AHI fails to capture the depth and breadth of sleep apnea across those three, at least across these three domains. And so if you look back at all the different metrics that were being proposed, essentially what they were doing was splitting apart these axes and looking at each one of them individually and creating a better metric across each one of those domains. So in ventilatory axes, study by Butler et al. Looked at event duration. Along the hypoxic axis, the hypoxic burden was looking at the area under, or you could call above, the desaturation curve. And in terms of the arousal domain, it was the arousal intensity, looking at the time spent awake during an overnight sleep study based on the EEG. And so all of these different metrics looked at the consequence of having an upper airway obstruction or a ventilatory disturbance, but there was no objective measure of the underlying ventilatory disturbance. And that's where we started. We said, let's look at something called the ventilatory burden or try and redefine the ventilatory disturbance in sleep apnea. And so we published the study in 2023, and I'll walk you through the main findings of the study and how we developed the ventilatory burden, and then sort of take you on from there. So the ventilatory burden is based on distribution of overnight breath-by-breath changes in airflow. For us, the airflow is the flow measured by nasal cannula pressure transducer system. It's automated and objective, and I'll show it has dose-response relationship with the level of obstruction in sleep apnea, and it may provide better utility for short-term and long-term outcomes in sleep apnea. So how do we derive that? First, we look at the nasal cannula pressure transducer system airflow that's measured. We detrend it. So any drift in the signal because of patient moving around or loose connections and so on are first fixed and the airflow is detrended. We then segment each individual breath into its inspiratory and expiratory parts. And in the inspiration part, we look at the mean mid-breath flow. So we look at the middle 1/3 of inspiration, and we look at the amplitude of the breath in that middle 1/3. And so we average that inspiratory peak. This is a surrogate way of deriving the peak of the breath because in real world cases, the peak of the breath is often corrupt or noisy because of either technological noise or physiological noise because of flow limitation, etc. So this was one way to normalize or not let the noise affect the calculations. Once we get the amplitude for each breath, we then derive what's called a normalized amplitude. So we represent the amplitude of each breath as a percentage of the preceding breaths. So if a patient study consisted of, let's say, just these four breaths, they are all very similar in height, very similar in amplitude, and they would all be quote unquote 100% normalized amplitude. If you suddenly had another breath that was reduced in amplitude, it would be, for example, 50% of normalized amplitude or something like that. So the next logical question is, I'm talking about sleep apnea. One of the main features is apneas when there is no flow at all. What happens when there is no flow, no breaths? How do you then calculate ventricular burden in those segments? And so during those events where there is no flow, we impute artificial breath. So in this snippet, for example, if there was no apnea, this patient would have had 5 normal breaths. And so we impute 5 breaths and give them a normalized amplitude of 0. And those are called zero flow breaths. So let's look at an example of how this looks like in a small snippet of an overnight study. And so here's the tracing of the airflow signal and the associated oxygen desaturation signal. This was a fairly healthy individual, and so they didn't have much sleep apnea, but you could see the variations in the amplitude over here, and you can make out that there is some disturbance underlying over here. If we then calculate the normalized amplitude, it looks as follows. And so the region in blue, we empirically found to be quote unquote normal or not abnormal breaths, and the region in yellow, which is less than 50%, are all considered to be abnormal breaths. And so they are candidate hypopneas or apneas. So for each breath across the entire sleep study overnight, we get the normalized amplitude, and then we use that amplitude to derive the ventilatory distribution. So we represent each of these normalized amplitudes as a histogram. And based on the sort of experiments we did, we found that the proportion of breaths less than 50% of normalized amplitude, that is breaths in this yellow region, is what is sort of abnormal. And we termed that as the ventilatory burden. And so for an individual, ventilatory burden represents how many breaths overnight are less than 50% normalized amplitudes. And to give you a scale, overnight for any individual, there's about 7,000 to 8,000 breaths. And so this histogram represents about 7,000 to 8,000 breaths overall. So once we had the metric and we thought it's actually representing the true underlying ventilatory disturbance, we then proceeded to do a series of experiments to derive sort of the different ranges and its test-retest reliability and so on. So first question we had was, what is the normative range? What is considered normal and abnormal for ventilatory burden? This was never done with AHI. Most of the AHI sort of measures were, there was a historical context for it, but it was just derived based on, some simple experiments, but not very sophisticated systematic investigation. So we attempted to do that with ventilatory burden. So we used the Episono normal cohort. So this was an Sao Paulo epidemiological study. So it was a study in Brazil conducted over 1,000 community individuals, out of which about 100 of them were deemed to be normal subjects or healthy controls. They were free of any known diagnosis of sleep disorders or sleep complaints. They were not sleepy at all. Their fatigue scale was very low, or the value on the fatigue scale was very low, and they did not have any significant primary lung disease. And so they were truly, quote unquote, healthy controls. And one of the best ways of deriving the normative range was asking what was the ventilatory burden in this cohort. And so when we look at that, it was about 100 individuals. Their distribution looked like a bell curve or a normal curve. Most of the breaths were centered around 100% normalized amplitude, as you would expect. And then very few, I would say, in the hypopnea range because of REM sleep or something like that. When we looked at the ventilatory burden values, not the histogram, but the values across all the individuals, 100 of them, we saw that the 95th percentile was at around about 20% or so. So if the proportion of breaths overnight that were reduced amplitudes, 50%, was more than 20%, we call that abnormal. And if it's less than 20%, we call it normal. This was one cohort. And so we asked the question, what is there another cohort we can sort of validate this and ask the question, is it same in another cohort as well? And so we had another study ongoing, which was called the DAFN study. And as part of that study, we also had a normal cohort, which was consisting of healthy volunteers in the New York region, about 22 of them, who had regular sleep-wake schedule. They were not on any drugs or receiving any treatment for medical conditions. And when we looked at their ventilatory distribution, it appeared to be the same. It was a normal bell curve with 100, most of the breaths centered around 100% normalized amplitude, and very few in the apnea or the hypopnea range. And when we look at the value of the ventilatory burden, there was no significant difference between the two groups. And again, most of them, the 95th percentile was closer to 20. So that gave us confidence in the cutoff of 20 as a normal, abnormal ventilatory burden value. The DAFN study that I just mentioned also had an OSA cohort. So these were clinical patients with sleep apnea or suspected sleep apnea who came through the clinic and then were treated and went through series of experiments. And so that was a convenient sample for us to look at how does ventilatory burden behave now in people with actual disease. And so this was the spread of ventilatory burden values in 92 sleep apnea patients. When they got treated with continuous positive airway pressure or CPAP, their ventilatory burden values, as expected, reduced significantly and went almost below 20 for all of the subjects. And that was kind of, again, I would say, what we had hypothesized based on the previous data I showed, that the normal ventilatory burden was relatively lower than 20. As part of that study, there was another visit where their CPAP level was reduced by 4 centimeters water. And so when you do that, you create what's called suboptimal CPAP treatment. And so it's not enough to cause apneas maybe, but sufficient enough to cause either a flow limitation or hypopneas. And when we do that, you can see that ventilatory burden starts to increase. And when they had another visit where treatment was completely withdrawn, ventilatory burden went back to their normal levels. And so this kind of shows the dose-response relationship with the level of obstruction. Artificially doing it by CPAP, by manipulating it, we see that as and when the level of obstruction increases, so does the ventilatory burden. And again, this is the same graph, but looking at the histograms as well. So as expected on CPAP, they look very normal. Most of the breaths are centered around 100% normalized amplitude. And then as you progressively go toward eliminating CPAP, you can see that the ventilatory distribution returns back to the baseline shape. We then asked the question, what is the test-retest reliability of this metric? So as we were developing this metric, we were asking the question, is it stable night after night, or does it change? So we had a convenient sample of individuals who came to the sleep lab for another project doing consecutive night polysomnography. And it was about 70 in lab. And as part of that study, 135 did multi-night sleep study at home. And we looked at the ventilatory burden in those individuals, and both across in lab and home, we found that the intra-class correlation coefficient was pretty strong and suggested that it was stable night to night under stable conditions. There was some variability, but most of that was attributed to position changes throughout the night. So once we did the face validity and we looked at the different, reliability measures and so on, we then asked the question, how does it relate to the outcomes? Because as you recall, that was the main question for us, is AHI was a poor predictor of outcomes. Is ventilatory burden a better predictor or not? So we went to the Sleep Art Health study, which was a multi-center community-based prospective study. About 6,400 men and women aged 40 and older were included in the study. And the baseline sleep study was done around 94, 95, and its data was made available by the National Sleep Research Resource. All of the individuals were followed for long-term outcomes. And so cardiovascular mortality, the average follow-up was about 6 to 7 years. And so these were deaths specifically due to cardiovascular disease. They also looked at deaths due to any cause and was called all-cause mortality. And that was with a follow-up of about 8.2 years. The Sleep Art Health study had at-home PSG and it did include EEG. Airflow was measured using the thermistor, not the nasal cannula pressure transducer system, but the thermistor. They also had chest wall and abdominal movement signals using the respiratory inductance plethysmography RIP belts. And both of these signals were used by manual technicians to evaluate apneas and hypopneas. So it did not have the nasal cannula pressure transducer system airflow, which, as you recall, was one of the basic requirement for evaluating ventilatory burden. So what we did was we knew that you could derive flow from volume, and the chest and abdominal bells gave us a surrogate volume measure, not a very accurate one, but some surrogate volume measure. And so we attempted to derive flow from volume by differentiating volume. So we went back to the Episono cohort of healthy normals first to develop the methodology. They had both the chest abdominal signals and had a volume signal as well that was calibrated. And they also had the nasal cannula airflow signal. So what we did was we compared the actual nasal cannula airflow, which is at the top over here, and our own derived flow, which was differentiated, just the derivative of the volume, and looked at and sort of compared the two. And visually, the shape-wise, they sort of, looked very similar. The sampling frequencies were different, so that's why one of them looks very smooth and the other one is sort of more noisy. But when we did sample by sample correlation, so each individual sample on the breath was correlated with the actual value, we saw that the correlation was very high and it gave us confidence that perhaps this could be used in the sleep art health study. When we looked at the distribution in the Episono cohort, the ones I showed you before, with either the flow-based ventilatory burden or the chest abdominal-based ventilatory burden, they were very identical. So the similarity metrics were very low in them. These are actual examples from the sleep art health study. So this one tracing where oxygen saturation is at the top, thoracic and abdominal belts are at the bottom, the thermistor, and then this is the flow that was derived based on the thoracic and the abdominal signals. The red boxes were the manually marked events by the technicians. And so you can see for our cases, the amplitude variations were actually pretty easily detected, and we thought this could be then used in the calculation of ventilatory burden. Here's another example in someone who had severe disease. And so you can see again, even with the thoracic abdominal belts, you can make out apneas, hypopneas. And with the flow RIP, which is using the belts, you can also make that out easily. So after removing, missing data, covariates, etc., we had a total of about 4,700 individuals with data for all the different variables that we needed, and about 1,000 of them died due to mostly cardiovascular causes, but there were other causes as well. In terms of cardiovascular mortality, we had about 4,100 individuals, out of which about 300 died due to cardiovascular disease. All comparisons we did for this particular experiment were against the AHI-4. AHI-4, as you recall, contains both the ventilatory and the hypoxic component. So it's looking at the apneas, hypopneas associated with 4% desaturation. So for our case, when we were comparing with the AHI, we only had the ventilatory piece. We did not have the hypoxic piece. So we then proceeded to also create or develop the automated hypoxic burden. And so we took inspiration from the study by Azerbaijan et al., which looked at manually marked respiratory events and looked at the oxygen desaturation area associated with each of these events as the hypoxic burden. So in their paper, they looked at these manually marked events, calculated the area above the saturation curve and bounded by the baseline, and called that the hypoxic burden. We derived an automated version of it where you did not need manually marked respiratory events. And it was basically looking at the area again above the desaturation curve, joined by the left and right peaks. And when we compared test-retest reliability of this metric, we did all sort of the same experiments as ventilatory burden, going through each individual step, and saw that it had face validity and was behaving as we expected. So here's the relationship between ventilatory burden, hypoxic burden, and all-cause mortality. So to start with, I'm going to have you focus on just the concordance metrics. It is very similar to the goodness of fit when you're doing a linear regression, except in this case, it's Cox proportional hazards. So AHI4 was a significant predictor of all-cause mortality. When you look at ventilatory burden, it had a significantly greater predictive ability, and we divided sort of this was the hypoxic burden. Hypoxic burden was divided across different quintiles. So we took the entire data, split it into 5, and then looked at the quintiles. When we compared hypoxic burden plus AHI, we did not see any improvement, which makes sense because AHI4 already accounts for hypoxic piece, and so you wouldn't expect any increase in predictive power. When you look at ventilatory burden, it was significantly better than AHI, very similar to hypoxic. And when you combine the two, ventilatory and hypoxic, you saw the highest concordance metric, indicating that that was the best fit in terms of predicting the outcomes. We also looked at cardiovascular related mortality, and the same story followed, where when you combine ventilatory and hypoxic burden, it significantly outperforms AHI4 in predicting these outcomes. So to recap, AHI4 contains the ventilatory hypoxic piece, but was combined in a very rudimentary way. When we separated it and developed our own metrics that were more automated and objective in a way, and combined them, it was much better able to predict outcomes than AHI4. These were the adjusted survival curves, again, depicting the same sort of story with ventilatory burden. When we looked at the association of ventilatory burden with age, gender, BMI, AHI, hypoxic burden, we saw various degrees of correlations. The one that was most notable is that hypoxic burden was highly correlated with AHI, whereas ventilatory burden was moderately correlated with AHI, not as high as hypoxic burden. It was also associated with daytime sleepiness. As I said, one of the biggest complaints in sleep apnea patients, we calculate using the Epworth sleepiness scale. Also associated with hypertension, and so was the hypoxic burden in those cases. So just summarize, I looked at all the different sort of components of AHI, ventilatory, hypoxic, and arousal, and showed you that when you combine them using traditional statistics, they perform better than AHI in predicting outcomes. But if you recall, across all of these domains, we looked at only single metrics or a single number. So the question then rises is a single number sufficient descriptor of the disease? If you recall, we had the same issue with AHI where it was a single number trying to predict the outcomes and several different outcomes for the same disease. And we saw that it was severely limited. So are we going down the same road when trying to predict outcomes using these different metrics with a single number? So that's where the idea for a ventilatory distribution came. And so here are some example subjects, and in this case, 4 subjects with the exact same AHI, 24, different ventilatory burden values. But if you look at the distribution of the breath by breath amplitudes overnight, their shapes are very different. And so these 2 individuals, which are very closer, 22 and 28 for ventilatory burden, have a very different shape. One has roughly equivalent apneas, hypopneas, whereas another one has much more significantly higher apneas as compared to hypopneas. And so this led us to ask the question, can this distribution be used to actually predict outcomes and not just a single number? And that's where the sort of idea came to us for using AI or machine learning based approaches. So before I go to that, I'll also go through quickly for hypoxic distribution. Again, the same idea there. These were 2 different subjects who had similar AHI, similar oxygen desaturation index, which is just the frequency of desaturations. But if you look at the shape, it's very different. One desaturates to 85, another to about 90 or above, yet they have the same values. And so you could actually do the same approach that we did with the ventilatory burden, looking at the histogram. You can look at the histogram of these desaturations. And this could potentially distinguish between individuals with very similar hypoxic burden values. And so lastly, the third piece was the arousal burden. And I haven't discussed as much about what to do with the arousal burden. So there were several ways to quantify arousal burden. One is the arousal index, which is just the number of times a sleep apnea patient woke up overnight and just calculate that as an index. The study by Sharda et al. Looked at cumulative duration of arousal events relative to total sleep time. There were newer sleep depth metrics, such as the odds ratio product. And the odds ratio product looks at the ratio of delta power, alpha power, in terms of the spectral power analysis of EEG, and tries to determine what percentage of time does a sleep apnea patient spend with very deep sleep or in full wakefulness, and tries to sort of use that as a phenotype. We also looked at an EEG measure called the slow wave activity surrounding K complexes. And so we went throughout the night, looked at K complexes overnight in the EEG, detected them automatically. And we looked at the activity right after a K complex. And we saw something interesting in that those who had more alpha right after a K complex had actually more lapses in vigilance or were not attentive throughout the day, whereas those individuals who had more delta activity right after a K complex had actually, much more, were much more attentive and had very fewer lapses in vigilance. And so that was one of the predictors we were using for sleepiness or vigilance, and we wanted to use that as a surrogate for arousal burden. So all of those were the components for physiology-guided AI. So our hypothesis is that this is a means to combine the different burdens. So if you think about it, you have histograms across different predictors. Each histogram has about 20 to 40 bins. And if you were to combine that in a traditional statistical model, it's very complicated and it doesn't take into account nonlinear relationships between those, I would say, different histograms. And so that's why we propose to use a machine learning model, but not just one model to combine all the predictors, rather use a model that is different for different outcomes. And so the weights by which you combine these different histograms are going to be different for different outcomes. And so you get through that probability of having significant OSA, probability of sleepiness, cardiovascular outcomes, mortality, and so on. And then you can combine all of that to actually stage the disease. So just like cancer, for example, probability of significant OSA would mean that they have some underlying disturbance in sleep apnea patients, but not necessarily at risk for adverse outcomes. But if they start to have high probability across all of these different models, then you can say that they may be at stage 4, for example, where they have a high risk for all possible outcomes. And so that's why we again went to several different large data sets. And after combining them, we had about 11,000 sleep studies that were used with 70% training and 30% testing. The predictors were again the 3 components: ventilatory, hypoxic, and arousal. And we had the histograms across all of those features. And the first outcome we started with was sleepiness. So this is a questionnaire-based outcome, and it's a binary variable. Either you're sleepy or not sleepy, and that's what we sort of used. And we saw a very high AUC of about 0.8 as compared to 0.5 with AHI4. But more interestingly, we saw the features that were top in the model were sort of what you would expect. So for example, apneas were related to adverse sleepiness. High hypoxic burden was related to adverse sleepiness, drowsy awake. So if the subject was awake, but the EEG showed drowsiness, that was also more sort of hazardous. But if they had more deep sleep or more normal breaths, they were sort of in the protective category. So what does that mean when we try to predict the sleepiness from a polysomnography study? What it means is that the sleepiness mechanism is actually something that can be extracted from a polysomnography study. And so you see abnormal polysomnography features or sleep study features relate to sleepiness. If you were to normalize those abnormal features, then sleepiness should also resolve. And so in the pilot data we had for that study, we saw that those subjects who were sleepy and were treated with continuous positive airway pressure for sleep apnea, their baseline sleep study had abnormal polysomnography by our defined features. And so as you improve the polysomnography features, you also improve sleepiness. We then trained another model to look at the all-cause mortality. So again, this was about 5,000 subjects, and about 1,000 of them had died. So that was the event count we had. We used the same set of predictors, but the outcome now was a binary death or alive from any cause, including cardiovascular disease. And again, we saw a very high AUC of about 0.93. It's probably overfitting at this point. It shouldn't be that high. But nevertheless, in terms of mechanism, we saw very interesting findings where high hypoxic burden or a high amount of large breaths. So large breaths are in response to small breaths. Were hazardous, whereas if you had a good amount of deep sleep, it was more protective, and so on. And AHI4 was not better than, I would say, at random prediction. So to summarize the first part of my talk that I sort of gave, ventilatory burden and the distribution, I hope I've convinced you that are better descriptors of the underlying ventilatory disturbance. They are objective and automated. They are biologically plausible, has good test retest reliability. They better classify long-term outcomes. And when you combine that with arousal and hypoxic burden, so the similar idea, you can have better prediction or classification of outcomes than AHI, which is the implicit combination of those components. And so what are we doing next to build upon that? Well, 3-axis was the start, but then we also have autonomic changes that happen during sleep, especially in sleep apnea patients. And so we want to add all the other different burdens. We are continuing to go towards explainable AI. So the features you saw, how do they relate with the different outcomes? What is the variability in those features is what we are trying to sort of explore. We want to assess the robustness to missing data or bad quality signal. Sleep studies are 8-hour long. During that 8 hour, many things go wrong. And so bad quality signals are inherent in the sleep studies. We also want to validate the model on a clinical population. So all the studies I showed you were epidemiological studies done in the 90s or 2000s and had, sort of a lot of data, but not clinical sleep apnea patients. Yeah, definitely. Yeah, no problem. And so we want to add other different measures to, sort of stage sleep apnea and look at, the different stages that I described. And so I'll touch a little bit about generative AI. Let's skip the autonomic burden for now. And so our current work is going to validate this entire model in a clinical population, but we are not just using the physiology-based predictors, but also adding generative AI-based models that extract symptoms from clinical notes. And so for all the sleep apnea patients that get evaluated through the clinic, there's a extensive history that is being evaluated or characterized. And so we want to use that history or past medical history to then ask the question, do those symptoms with the physiology measures, are they able to better predict the outcomes? And so this is ongoing work where we are trying to use generative AI models of our own to extract the symptoms from clinical reports. And so here's an example of a report and the prompt we provide to then extract the information we need. And so I'll skip that and just quickly go over the educational tools that we are using or attempting to develop using next generation AI. And so as part of my previous sort of slides, you saw that we have a lot of data, and sleep medicine is a field where there is no scarcity of data. It has a lot of data. And so perhaps we can use all of that data to build educational tools. There's simulation in many different fields of medicine, cardiology, emergency, and physiology. But in sleep medicine, there's actually no simulation. There's static case studies, and it's all based on error-based learning. So someone makes a mistake, and then you learn, and you have to wait overnight for someone to actually make a mistake, and you have to have many sleep studies be evaluated to do that. With journal reviews time being slow, again, it's not optimal. So if you have case reports and everything that people learn from, publishing them in journal is very slow, and it's not easily shareable across institutions. So we are attempting to circumvent those problems by building a sleep simulator. And so it's a nocturnal polysomnography simulator. At its core, the idea is there's two displays, one controller and a display. The controller allows one person or the same person to modify parameters of the polysomnography study, and then the display is just showing the display. So you could have events over here. So what happens when if continuous positive airway pressure mask has a high leak, what happens to the polysomnography or the airflow and so on. And so you could attempt to do all of that. So far we have used about 30,000 or so studies, actually closer to 50,000 studies to generate EEG segments. So we fed all of this data into a generative AI model that we trained to be able to generate synthetic 30-second EEG data. And that was based on sleep stage. So we provide a sleep stage and it predicts or provides for us a 30-second EEG segment. And so here's an example where the top and the middle are real non-REM stage 2 EEG and stage 3 EEG, whereas in the ones in the highlighted region are the artificially synthetically generated. And when we looked at the spectral power decomposition, it was very similar to the real EEG. And then we added our own sort of, measures into it where even after you generate the EEG segment, you could tune the delta in it, the alpha in it, and sort of present scenarios to technicians and fellows and see how they respond to those different scenarios. In phase two, what I showed earlier was the EEG, but we are using the NUMA model by Michael Cohen et al. To integrate that into our sort of sleep simulator as a cardiorespiratory model. This is not an AI model per se, it's not real time, but it has features that could be important, for example. And so this was all built in MATLAB Simulink at that time, and we are trying to port it now to our sort of next generation interface. But what it allows you to do is sort of predict all different theoretical possibilities of scenarios. And so on the left screen over here, you have the overall cardiorespiratory display. And on the right, and you can go even sort of fine tune into it, but on the right is more respiratory system. So you can look at airflow, breathing rate, ECG, etc., and see how it behaves with changes in different parameters.
Sir, can we wind up? Okay, summaries.
Yeah,
Okay.
definitely. Yep, no problem. And so far I've shown you that, one of our main aims has been to develop physiology-guided AI models for predicting outcomes. And the way we do it is we used physiology-guided features from raw polysomnography data. And so rather than just feed it as a black box, we try and use known physiology and their features to extract what we need. And when you combine them using AI ML methods, it can better predict outcomes than the standard ones. We can also extract physiology-based information from clinical notes, and then perhaps it can augment the prediction. And lastly, with next generation AI ML techniques nowadays, you can actually build educational tools by taking all of that sleep data, training it into a transformer-based architecture or classifier, and then synthetically generating all of that data. So with that, my entire team and I thank you sincerely for taking the time to listen to me, and I apologize for not being there in person. And a big thanks to Dr. Gupta and the organizers for making this possible and giving me an opportunity to share our work with you.
Thank you so much, Dr. Ankit, for that incredibly insightful and engaging lecture. Your expertise and the innovative approach you have shared have truly broadened our understanding and inspired all of us here. So we really appreciate you taking the time out to join us virtually and contribute to the success of this conference. So may I now request
So much for the invitation.
may I now request Dr. Latika ma'am to please felicitate our keynote speaker virtually.
Um, Thank you, Dr. Parekh, for a absolutely wonderful presentation. It was a very elegant talk and very beautifully explained how we are developing multimodal AI and new indices to improve patient care for diagnosis and prognosis of patient care. So this was a wonderful presentation. I had one... okay. I just wanted to also congratulate him because it was so. I don't know whether you'll be able. Where is the camera? Can you see?
Yeah, I can see.
Okay, yeah.
I can see.
So, congratulations and thank you for a wonderful talk.
Thank you so much.
Yeah. All right, there you go. That's it. Very unfortunate you couldn't join us. It was. It would have been great to have you in person.
Definitely. I hope the next conference I'll definitely join.
Surely, sir. We'll wait for you.
Definitely. Thank you so much.
Thank you, sir. Thank you so much. I now request Dr. Supriya ma'am to please felicitate Dr. Latika ma'am, our chairperson. I request Dr. Shobita ma'am to please felicitate Dr. Michael. Requesting Dr. Kiranmai ma'am to kindly honor Dr. Michael, please. Dr. Shobita ma'am, sorry. Dr. Shobita ma'am. For a next session on high-density EEG features as brainstem classifiers using AI tools, I would like to take the opportunity to invite our esteemed chairpersons on stage. Dr. Renuka Sharma ma'am, Director, Professor, Department of Physiology, Vardhaman Medical College, New Delhi. Ma'am has more than 23 years of teaching experience and has been the founding faculty in charge of undergraduate academics and internship programs. Ma'am, we welcome you on stage, please. With a big round of applause. Our second chairperson for this session is Dr. Mona Bedi ma'am, Director, Professor, Department of Physiology, Maulana Azad Medical College. Ma'am has more than 25 years of teaching experience and her major focus of research is autonomic functions. She has also authored 3 textbooks on practical physiology. Welcome, ma'am. Our third chairperson, Dr. Supriya Gupta ma'am, HOD, Physiology Department, School of Medical Sciences and Research at Sharda University. Ma'am has more than 30 years of experience here. I now invite our speaker, Dr. Ratna Sharma ma'am, to please come on stage and deliver her lecture. Dr. Ratna Sharma, Professor and Head, Department of Physiology, AIIMS, New Delhi, is a very senior neuroscience researcher. She established SCL at AIIMS, New Delhi, with an aim to study the neural basis of cognition in healthy individuals and explore the brain states associated with altered performance in neurodegenerative and neuropsychiatric disorders. Some of notable contributions of SCL includes deciphering EAL microstates as a predictor in working memory tasks with increasing memory load, binocular rivalry, and envisaging microstage patients with schizophrenia, Parkinson's disease, glaucoma, ADHD, and major depressive disorders. Professor Sharma is a recipient of the prestigious AIMS Excellence Research Award, and her extensive research funded by DHT, DPT, and ICMR has culminated in over 70 research papers and 150 abstracts in national and international conferences. Her vision is to develop a platform for screening and profiling of patients with psychiatric and neurodegenerative disorders using QEEG analysis to develop state and trait biomarkers to predict the cognitive behavior and brain states. With a resounding cheer, I welcome Dr. Ratna Sharma ma'am.
I'll change from here. This is not working. बताया ना? It will work. आगे. यहाँ से भी कर दो. Doesn't matter. Okay, no problem. It's fine. Good morning, everyone. First of all, thanks to Dr. Supriya for, Thank you, ma'am, for inviting me for this prestigious conference that you are holding so well. I can see it already. No. So, those of you who know my work know that we work on quantitative EEG and try to understand the EEG or the neural correlates of stress, cognition in control subjects, that is normal population, and subjects with psychiatric and neurodegenerative conditions. Okay? So, for this, no, it's not working. So for this, you can just try this, I'll keep speaking. So for this, we have been studying we expose the patients or the normal subjects to cognitive tasks, and then we record 128 channel EEG during rest and during the cognitive state. And then we try to see how the states differ, like I've reached here. So this is how we study during the resting state compared to the cognitive state. So most of my work in the lab is related to this kind of analysis. But I would accept one thing here, or I would very proudly say here, that whatever we do is dependent on that one fine student who enters your lab. So this work was the result of 3 or 4 initial PhD students, one of whom is sitting here, Dr. Sunaina, who brought the work to a level where we could publish very comfortably. And then came a student who wanted to study, could human brain control the mechanical body parts or exoskeleton? I had no experience, and I still don't have experience in AI machine learning tools, but we do know what the input could be or what physiologists are important. The student was Dr. Siju. He was MBBS from AIMS and he wanted to study this. So we started first working on what physiological signals could be used for the movement of mechanical devices in amputees, for example. Like, this was the question with which he came. The discussions went on, what could be the strategies to handle this? Which signals can we pick up? Could it be central nervous system to the periphery, that is the signals which are going to the muscle, or compound action potential, or EMG in case of non-amputees? Like, you take the EMG, convert that into a mechanical, give it to a mechanical device which will work. But then the best option we thought was, since we were working on EEG, the thought of movement for controlling the exoskeleton would be a good idea. Like, we know, we teach undergraduates that as we want to move something, it is the thought which comes first and then it is translated to the actual movement. So for this, there is a concept which is known as motor imagery, which is cognitive rehearsal of a motor action without actually executing it. So all of you can imagine right now, you are holding this mic. You can always imagine it without actually holding it. So the thought of this, it seems, starts in the prefrontal cortex, leads to a series of neural activities in first the premotor, then the supplementary motor, and finally the motor cortex. So what has been shown is that whatever happens during an actual thought is the same as that which happens during the actual movement. So the neural signals for the two are supposed to be similar. And one important aspect is the desynchronization, the last point, the ERD of the mu rhythm. So event-related desynchronization of the mu rhythm, which is 8 to 14 hertz, is what happens when you either execute a movement or think of executing a movement. Fine? So you can imagine what a simple solution to this problem, that you think about something and you execute it through an exoskeleton. So the type of analysis we were doing was, you record during the resting state and then record during the thought of a movement or thought of a limb, and record the ERD and use the signal for exoskeleton. But the EEG is a very complex data. And you can imagine the thought and the actual movement from the motor cortex and that to EEG, non-invasive recording, how subtle the signal would be if you record it from the EEG. Which has, so a normal statistic or a series of statistical tools will not be able to solve the problem. Therefore, we decided that we will use AI methods to decipher the signal for the thought or the actual movement of the limb. So the aim was to create a brain-computer interface-based EEG data of motor imagery using machine learning algorithms, and also give a feedback through the mu rhythm ERD. I'll just come to it, it will be clearer. Finally, for the consumers, it is to create a prototype of a prosthetic forearm, that is a robotic limb, capable of performing movements that will enable a subject to grab, like grabbing this microphone, and lift it, which is very important for day-to-day activities. So this is the flow chart which you will, if you want to really listen to me throughout the lecture, you will have to understand this one slide. So what we want is the person imagines the movement of grab and lift. We record the EEG, and in the EEG we are recording the desynchronization of the mu rhythm. Find the hidden pattern in this rhythm and feed it to an exoskeleton. So this exoskeleton will be able to perform this grab as well as lift motion. So this was the basic aim. And this, like, if I say I'm imagining this, it will be more effective if I can actually see in a exoskeletal or some movement that actually whatever I thinking was leading to that thought. So what we decided, I will just run this again. What we decided was to use this movement as a feedback to the subject. So when I think of grabbing, the machine goes like this. I know my thought process was good, fine. It led to grabbing, and vice versa for lift. So what we needed here was the brain-computer interface, which is defined as it gives users a communication and control channel that do not depend on the body's or the brain's normal output channels. That is, you're not using the limbs, you're using a mechanical device for doing whatever the brain wants to do. Fine? So BCI basically consists of these three components. First is the input, which in our case was the thought. Then you acquire the signal of that thought, let it undergo these processes, which is pre-processing, classifiable features. What features from the EEG will we pick up to define grab as grab and lift as lift? Fine. So these are the classifiable features. And then play with the rhythm. Which algorithm or which classifying algorithm is working for you? So these three components are the ones which will require experimentation. So we would experiment with these processes, and then we will have the machine output, that is that mechanical device that I just showed you. So this is what was the basic work that led to a PhD, and that is why I am here. So again, motor imagery, record the EEG, find the hidden pattern, let it be converted to a mechanical output, and let this feedback result in a better motor imagery. You understand the circuit now? So once a digital signal of the thought process is acquired, a classifier will be used to decipher the hidden and the invisible pattern. It's hidden and it is invisible. These are two very important things. Results of these classifiers could then be translated as a machine response. The response can further be used as a feedback to improve the motor imagery. So I have repeated it 2-3 times for you to understand it. Why EEG? So the question was, could we record the EMG or EEG? EEG is a very noisy system, we all understand it. However, the subtle changes that are present in the EEG during, let's say, grab or lift, it's just a challenge. It was a challenge for us that could the grab and lift signals be different from the control signals or the baseline signals, or will it lead to a good machine learning output? So the two movements that we decided, I have already said, were the grab and the lifting of the hand. And remember, these two are very close to each other in the motor cortex. So the challenge is even bigger. Fine? So then the question is, I mean, there are many engineers sitting here, I suppose, from the engineering background. For them, if it is so easy, I mean, we can ask them, if it is so easy that you can convert a thought into a mechanical device, then why haven't we still got such a system? The reason for that is the low signal, first of all, we want it non-invasive. So it has to be EEG, not the intracortical recording, which will be more precise, less noisy, but that is not possible, that is not done. So we want EEG, which has low signal to noise ratio, and mind you, huge inter and intrapersonal variability. If I am talking to you now with this commotion going on here, or 2 minutes back, there will be a difference in the electrical activity. So my EEG will be chaotic, fine? But I have to extract this pattern regardless of what the baseline situation is. So that is another challenge that we have. So same person and another one of you comes here and talks will be very different. And high dimensionality curves. The EEG has lots of dimensions which I'll just come to. So that is another challenge that leads to this problem that we do not have an exoskeleton which can be run by the thought so easily. So these were the tasks to be accomplished. I will just go through the tasks rather than enumerating them here. So this also I have talked about. So these were the sensors that were created. This was for the grab motion, then lift. This was coming as a challenge that we were not able to record this. So you just have this light source, and the cutting of the beam was taken as lift here. And this was connected to an Arduino, and the output of this went to the computer to classify the grab as well as lift. This was the first draft of the robotic arm, which I have already shown you. This is how it came out. And this is what it could perform. I think there's a difference in the Mac and this system. So it does show you that this is capable of holding this glass and picking it up. Doesn't matter. I think we'll skip this. There's another one which I would want to show. Just forget about this. So while the person is doing all of this, we will record through this electrode net, which has 128 electrodes. And to localize the cortical activity, which also we did, although I will not be talking about it in today's presentation, we have this cameras mounted, which can tell you the exact location of the electrode in each subject. So we recorded mu rhythm desynchronization, and this is the details about why we should record mu rhythm. Then we took 91 subjects for this study, and this was the interactive board which was used to give instruction, because we are not talking about one or two or few trials. We are talking about hundreds of trials. So these are this is the interactive board which gave instruction that whether you have to do actual movement or you have to do motor imagery of either grab or lift or both. So whenever randomly the computer will be giving input to this interactive device, it will sometimes be the bulb for the motor imagery will light up, then grab will light up, so you will do motor imagery of grab, or you will do actual movement of grab as well as lift. So this is the board which is going to give you instructions. And also, as I told you earlier, and I'm repeating, whether you could do motor imagery or not will be given you as a feedback by the movement of this device. Okay? So you will know how well you are doing, and although because of lack of time, I will not be going through the details. So in one of the groups, we decided to analyze the results further, in which the feedback was given, because we realized that when you give the feedback, the motor imagery improves. Right? So the subject comes, you place the electrodes, and you replace also the EMG electrodes. And then the training session begins. You cannot just start doing it. This is how the experimental protocol is. You train the subject for the 3 types of movements, that is grab, lift, and grab plus lift for 10 times. Let the person do the actual movement, and then the person will do 3 types of imagery. Fine. So after this, the EMG electrodes, if you can imagine why the EMG electrodes are there. Anyone? That is to rule out muscle activity or movement during motor imagery. Fine, because we want the thought to be thought, not actual movement, because that actual movement is going to be used as training data for classifying the motor imagery. So motor imagery is very important. It does not have to be associated with the actual movement. And when we did this experiment in the initial times, just open it. When we did it in the initial subjects, we realized there were 2 groups of individuals. Those who could perform motor imagery and those who could not. So there were some individuals, however hard you try, they were not able to perform, so they were excluded from the study. So this EMG helped us in deciding that, okay, it is motor imagery. So training consisted of all of this. First, the cue came for 3 seconds, then motor imagery. This was repeated a number of times, and when the subject was asked to perform the motor imagery, it was confirmed by 2 ways. One, by seeing the ERD of the mu rhythm, which we saw, then the EMG, that is absence of EMG, and the third thing was the subjective reporting of whether they could do motor imagery or not. So these were the 3 parameters taken to rule out any other sort of mixing up. So ultimately, now again this is important to understand. If you were, you remember in the last lecture also he was talking about that they used 70% of the data as the learned data, and we used actual movement data as the learned data. That means we gave this data to the classifier that when the grab, lift or grab plus lift happens, this will be the pattern. So the classifier will learn it. And then it will be used to test the 3 types of motor imagery. And this will be optimized, the classifier will be optimized for each subject. Okay, so it is a individual classifier that is specific to that particular person, optimized for that particular person. So what are machine learning algorithms? They are a group of algorithms which could be simple or they could be extremely complex, and they will classify the data from the previously fed grouped or ungrouped data. Okay, so we used a type of supervised learning algorithm. We tried 2, that is support vector machine and artificial neural network. I will just come to the results, which one we finally decided to use. Now coming to what does the algorithm do? Because I know most of the audience is physiologists, so I would want to spend a few minutes here. So if you have data, so this is some data, some random data. It could be classified on the basis of feature 1 and feature 2 as 2 different groups using this algorithm. That is understandable? Fine. So if it could be height or weight. Height or weight are 2 features which are classifying the subjects into 2 categories. Fine. So similarly, you could have, so these will be used as features, and then you will have an algorithm which will tell you whether it is, the person has high weight or low weight and so on. So if the same algorithm is used with lots of features and it uses lots of neurons, okay, different layers of neurons to decide what the output is, this is what is in ANN. Okay, as simple as that. And what we will do is, we will use, thousands of features of EEG as the features, use different algorithms. Here the example is ANN, and it will tell whether motor imagery was there or not, or it was grab or lift. So it will classify the data for us. So continuing with this, we used three groups of subjects. In one, it was only motor imagery. In one, there was motor imagery with just one feedback, whether you could do it or not. And in the third, we actually used the grab, that exoskeleton to tell them whether they could do or not. So I'm on time, I suppose you have. I have been instructed not to go beyond half an hour. So in group 1, no feedback is provided. Group 2 has only one node, yes or no, regarding whether motor imagery was there or not. And group 3 was whether it was one of the 3 types of motor imagery. So this is how it went. Group 3 was whether grab was there or not, and lift was there or not. Why do we do feedback? I have kind of told about this. It builds up confidence in the subject. It improves the subject's performance speed and results in EEG changes that improve classification. So what is our ultimate aim? To be able to classify it very accurately. Fine. So for that, it is important to give feedback. So I hope this runs, because this is something interesting. Yeah, it is running. So what is happening here? The subject is seated. Okay, it is working. The subject is seated, the EEG is being fed to the computer, and computer, if the person is asked to do motor imagery of grab, then the classifier gave the input to this exoskeleton to produce grab. And the subject sees that, okay, when I was asked to do grab, my EEG classified this, or it made to move this exoskeletal or robotic arm as grab. So this is the feedback that we are giving. Okay? Is it clear to all of you? So just see that once again. So it is lift, motor imagery of lift, and it is lifting, and it could be both also, as per the instruction given to the subject, whether he has to perform. And actually, if you can see, this is the hand here with the lift sensor and the grab sensor. So it is simultaneously, following the instruction. It is actual movement versus the motor imagery. So this is how feedback goes. So we have talked about the thought is there, we have taken the signal. Now we are going to play with the pre-processing of the data. EEG, is a very complex data, very noisy data. So how do we go about doing this? Okay, and one important thing which I wanted to tell you before I proceed is, so how do you quantify the classification accuracy? You see whether the class 1 positive is actually classified as positive or not, and so on. And ultimately, we will create this kind of a table, which is the way to present data for, it is called confusion matrix, which will tell us how much was the accuracy, sensitivity, specificity, and negative predictive value and positive predictive value of this particular classifier. So this is how we started. Now, this is what we are going to play with now. So in the pre-processing, we will use different bands. So we decided to use mu band. Mu band is 8 to 14. So it will filter the data from 8 to 14. And then it may use or may not use spherical Laplacian. This is just an algorithm to improve the localization. I mean, if I can just say very roughly, it improves the EEG data, fine. And then then there is discrete Fourier transformation, whether you want to use 4 or 3 or 2 frequency bands, and then which kind of classifier you want to use. So this is all of this was made in Xcode, and feature was pure DFT versus with or without principal component analysis. This is part of pre-processing. Laplacian versus no Laplacian. So these are the things we are playing with. Comparing different window sizes, we do not know how much window to take. You have to just play with it. DFT values as combined or as individual. So we have 129 channels. Data is coming from 128 electrodes and a common reference. You could take 500 millisecond window for, you keep on classifying every 500 millisecond window. And sorry, you are picking it up after every 80 millisecond written here, but the window size is 500 millisecond, and it is you are using this 500 millisecond window to find out the values of 8, 10, 14 and, 8, 10, 12 and 14 hertz of frequencies. Okay, so this data is coming to you continuously. Every 80 millisecond you are getting this data. And these are overlapping windows. So the total features that you are getting, the total variables in R terms that you are getting are 129 channels, 4 frequency bands, and 6, just a minute, it is 4 frequency bands and what was 6 channel frequency and bands, 4 frequencies and bands. So using this kind of a system, we tried to make these matrices wherein PCA was not used or used, which window size and which epoch size, and you keep on looking at the accuracy and other parameters. So from this we conclude use of PCA improved the accuracy only marginally. But previous data has shown that PCA improves classification accuracy, so we did use it. Then epoch size or window size, we decided that, we found that it did not affect the classification accuracy significantly, but there are reports that 500 millisecond prior to the recordable movement, the mu rhythm gets desynchronized. So we decided to use 1500. Then whether to use all the 4 frequencies together or separately. That was another way of looking at the data. So this is when they were taken as separately, this is when they were taken together, and we found out that DFT of different frequencies did not influence the accuracy whether they were used individually or combined. And spherical Laplacian did improve the accuracy of BCI, so we did use that. And then comes to which algorithm we wanted to use. We tried SVM, and SVM did not have, it could only classify baseline from motor imagery, but it could not classify grab from lift. And ANN could do that. Therefore, this is what the result of ANN is. It could classify baseline versus all movements, simple versus complex. That means simple is grab versus lift. And also it could classify within this grab versus lift also. So movement, one type of movement versus a complex movement, whereas, and also grab versus lift movement. So we concluded that SVM was able to classify grab versus eye open condition, that is the baseline condition, but was not able to classify movement versus pre-task data. ANN was able to classify grab versus EO as well as movements, all the 3 combinations it could do. So we conclude that machine learning optimized using EEG data of actual movement can be used to classify the EEG of motor imagery of simple and complex movements, and real-time feedback. For lack of time, I have not shown you the results of, I didn't prepare to show you the results of group 1, 2 and 3. But real-time feedback did improve the accuracy of the BCI. So what is the significance of the study? This is the study in which we are reporting for the first time that subjects' own EEG of actual movement was used as learned data, and it did improve, it did lead to classification accuracy. Classification of EEG of motor imagery of different types of movement could be done that are very closely present in the cortex. That was another very important, significant result. And third is classification of a simple and complex movements could also be done. So we could say whether it is only grab or grab plus lift. And fourth is ANN was optimized for each subject using patient's or subject's own data. So what is the application of this kind of BCI? Exoskeletal support or enhancement of paralyzed individuals, or even for soldiers, like enhanced contractions, etc. Functional prosthetic limb for forearm amputee. Controlling characters in virtual reality and games. I mean, this is just you can use the same kind of algorithms to get that. And controlling robotic surgery by surgeons. Now, this is with, after having confidence in being able to do this, now we plan to use the same kind of algorithms for classifying data in one of the studies where we are trying to assess the QEG signatures of long-term meditators, short-term occasional, then stressed subjects, and depression and schizophrenia. So we are recording EEG, we are analyzing the microstates in these individuals, and based on the microstate features, like microstates could have several features. Based on all of these features, we will try to run different types of algorithms to be able to decipher that this kind of microstates is present in people with long-term meditators versus stressed individuals versus whatever. So this is the group that I have. I'm very proud to have this group with me, and this is Dr. Siju Chako, whose work I have just presented. Thank you.
Ma'am, any questions, please?
So one bright student sitting here can make a difference. I mean, my capabilities, or anybody, all of us have limited capabilities, but when we join together, it can multiply. That is what I would say. Yes, it does happen. Like, I remember Siju as someone, whenever he used to come to my room, I used to say, oh my God. Like now he'll come with a problem and one has to solve it. So, but they challenge you. And having challenge in life is what keeps you going. Okay, thank you.
Hello, ma'am. I just have a question. Thank you for this wonderful presentation. I would like to know what is the clinical implication of this, that a thought process is being translated into a...
If you have an amputee, you can, that amputee can be fitted with this exoskeleton. He just thinks of, I mean, that is why we decided on grab. What is the minimum that we want a person to do to be able to grab a glass and drink water? So that is what he will be able to do. If he thinks, I want to grab, so this thing will go and grab. Now I want to lift, so I will be able to lift. That is the clinical significance of just this work. But it can be extended, and it is limitless then.
Thank you.
Thank you, ma'am. We deeply appreciate your time, ma'am. I request Dr. Renuka Sharma, ma'am, to please felicitate Dr. Ratna, ma'am. With a resounding cheer, please.
Please give. And somebody hold. Somebody hold it. पूजा, किसी को बोलो मैडम का ये रख ले किसी उसमें पैकेट. Okay, so I should also be there, I think. Yeah. वो कह रहा है मुझे मैम आप प्लांटर दे दो.
I request Dr. Supriya ma'am to please felicitate Dr. Renuka Sharma ma'am. I request Dr. Shobita ma'am to please felicitate Dr. Mona Baby ma'am.
रूपाली इसके बाद अनाउंस कर. एक एक पैकेट में करके मैडम, अच्छा मैडम लोग अपने आप कर लेंगे.
I request Dr. Shalini ma'am to please felicitate Dr. Supriya Gupta ma'am.
हाँ क्या?
Ma'am, your felicitation.
अरे मेरे को छोड़ो यार, देर हो रही है.
Please ma'am.
देर हो रही है, बहुत देर हो रही है ना.
It's okay, it's okay. She's like the prize mother.
Shalini ma'am. It gives me immense pleasure to announce that our chief guest, Dr. Gitika Khanna ma'am, is here with us. We welcome you, ma'am. We will now take a quick tea break, and we'll be meeting here for the next session as well as the inauguration ceremony in 15 minutes. The tea is waiting for you outside, please. For the next session, I would like to invite our three dynamic chairpersons, Dr. Deepti Nair ma'am, Professor and Head Microbiology, Vardhaman Medical College. Her research interests include TB and control of hospital infections, and ma'am has ResearchGate score of 1375.9 with a Google Scholar H index of 25. We welcome you, ma'am. Next, I invite Dr. Shoma Mukherjee, ma'am, Professor and Head Department of Pharmacology, School of Medical Sciences and Research, Sharda University. Ma'am is associated with this institute for years now. We welcome you, ma'am. Next, we have Dr. Dalip Kakru, sir, Professor and Head Department of Microbiology, SMSR. And sir is a very senior microbiologist and one of the pillars of this institute. Now it gives me immense pleasure to welcome our guest speaker, Dr. M. Michael Gromia, Professor, Biotechnology, IIT Chennai. His main research interest includes protein structure and function, mutational effects, and development of bioinformatics, data, and tools. He has published more than 280 research articles, 70 reviews, 8 editorials, and 3 books. His papers have received more than 17,000 citations, and his H index is 64. He is editor of BMC Bioinformatics, Bioinformatics Advances, and Frontiers in Bioinformatics. Out of numerous awards that he has received, I would just like to name a few. Oxford University Press Bioinformatics Prize, INSA Senior Scientist Award, Best Paper Award in Bioinformatics, Institute Research and Development Award IIT Madras, Outstanding Performance Award Tokyo, Tamil Nadu Scientist Award, and etc. He is ranked as topmost 0.5% of highly cited researchers in the world. He is an elected fellow of Indian National Science Academy, FNA. So with a big round of applause, I invite you, sir, to deliver your address on machine learning and AI-based methods for identifying disease causing mutations in proteins, applications to drug design.
Good morning. Thanks for the introduction. First of all, I would like to thank Dr. Supriya for inviting me to give a talk on what we are going in my lab in this meeting on physiologists. So I am not a medical doctor, but we are working on machine learning and AI-based approaches on disease-related problems. You listen to exciting talks on disease disruptions as well as EGG. In my talk, I will mainly focus on disease-causing mutations, specifically cancer-causing mutations. After COVID-19, so all are familiar with the term mutations. And after that, I don't have to explain what is a mutation. Before I go into details of my talk, I'll briefly tell what we are currently working in my lab. So I belong to the Department of Biotechnology from IIT Madras, and we are focusing on 3 different areas called the bioprocess engineering, computational biology, as well as medical biotechnology. And the main advantages of having different areas in our department is the collaboration among these faculties. And if you develop any algorithms or if you identify any targets, it is possible to validate using experiments based on a collaboration with other faculty members in our department. And my work is mainly on protein bioinformatics. So you are welcome to IIT Madras and our laboratory of protein bioinformatics. And we work on both basic research as well as advanced research. First, we try to understand the structure and function of proteins and their interactions, what factors which influence the structure or the stability or the interactions or aggregation and so on. And we develop various databases and tools to understand the structure and function. Utilize this information to specific applications like understanding the molecular mechanism of diseases. So what we did, so we worked on protein folding and stability. We developed various novel parameters, right? For example, long range order, which relates the contact between amino acid residues in a protein, right, and which is directly related to the folding rates. That means how fast or how slow a protein can fold from its nascent polypeptide to its folded state. And we developed various databases, for example, thermodynamic databases for the complexes, say protein complexes, protein nucleic acid complexes, and protein carbohydrate complexes. These thermodynamics are very important to understand the binding behavior, and we try to see which factors are governing this affinity of these complexes. Then we try to develop web-based algorithms to predict the binding affinity of these complexes, as well as how this will affect upon mutations. We did with this stability, say ProThermDB. It is one of the widely used databases in the literature, and you can say there is the first database I developed 20 years ago, and still we are maintaining with more than 35,000 data, and which received more than 2,000 citations. And regarding protein aggregation, because it is related to neurodegenerative diseases, so we try to see if we give a peptide whether this can aggregate or not. And the second issue is, in a protein there are few regions which are aggregating. So if we give a protein sequence, can we able to predict which regions are tend to aggregate? So for this we developed databases called the CPAD. This contains experimentally known aggregating peptides and proteins, and we try to understand the factors which govern this aggregation and develop methods to identify these aggregation prone regions in proteins. Okay, these are all for our basic understanding. Then we try to utilize this information, right, to the understanding the molecular mechanism of diseases, specifically on three aspects. Our lab is focusing on the disease causing mutations and structure based drug design, as well as we did a lot of works on COVID-19. Mutations, and some mutations which are responsible for various diseases. So now the question is, if there is specific mutation in any specific target, can we able to predict whether this is disease causing or it is a benign? So we developed databases called MuteHTP or HooverBase, right, for these disease causing mutations, and we related the sequence and structure based parameters with respect to the specific mutations and hotspots, and see whether there is a relationship between the structure or the sequence and the function along with these diseases. Right? This is our specific research focus in our lab. And if it is there, then can we predict a method to identify such disease causing mutations, and can we do with experiments? And the second aspect, that is on structure based drug design. So we use various drug targets. In the case of the cancer, we used EGFR and BCL2, mainly because the two faculty members, they are working on this area. So if you identify some mutations or some specific lead compounds, it is possible to experimentally validate using these laboratories. That is the reason we use these specific targets to address this cancer. Right? So then also this CS kinase in cancer. So that is a competition by Tokyo Institute of Technology, right? So they gave 2.2 million compounds, and they asked us to come with only 200 compounds that they experimentally validated. Yes, we used our bioinformatics approaches to identify the specific compounds. We screened and then we ranked the compounds, and more than 5 compounds showed the inhibition of more than 60%. This is COVID-19. So during the COVID-19, we also carried out analysis to understand the synergism of drugs, because during that time there was no drug or the vaccine in the initial point of time. So WHO, by emergency basis, they approved the drugs used for HIV as well as the flu. And the combination of the drugs works better than the single drug. So we wanted to see the synergism effect of these drugs. We found that these drugs bind to 3 different sites. It is not additive, but it is a synergism effect because of the conformational changes in this protein. We try to understand the specific mutations which cause this disease, as well as the working mechanism of the synergism effect of these drugs. Okay, so now I go with this my talk. Currently we are in the era of artificial intelligence and the big data, because AI needs data, and the big data is the huge initiative to collect the data on different aspects. In fact, the concept of big data came long time ago, because when the physicists they try to collect data, right, in CERN, mainly in terms of more than petabytes. Now the biologists, life sciences, they also joined in this group by the availability of the data based on genomics, proteomics, transcriptomics, as well as its metabolomics. So we have millions of data, right, to analyze. That's why we can also use the AI effectively with the various applications. One of the major breakthroughs in AI, it is the predicting the 3D structure of a protein. Right, as you will see in 2024 Nobel Prize, right, got for the AI as well as predicting the 3D structure, right, from the amino acid sequence. Right, DeepMind group, they used the data available in the PDB and they developed the method to predict the 3D structures of proteins, as well as they used to design the proteins. They got Nobel Prize in 2024 in chemistry. Okay, now the data are available. So then how to use the data and how to interpret the data, because it is very big challenging to use huge data, because we need to have huge computational power and we need the space to store this data as well as high memory power to handle the data. So during that time they started various initiatives by NIH or using this UK, the 100,000 structures, as well as in China they created initiatives to analyze more than 1 million data. During that time, in India, we used the OSCAT, that is the open source consortium for computer-aided drug delivery. So it is to collect the existing resources as well as the tools, so that anyone can use this for analyzing data or interpreting the data, rather than making a code for everyone in the different labs. Fine. So what are the big challenges in this handling this big data? So mainly the creating the analytical tools, solving scientific puzzles, accessing million gigabytes of data, and specifically overcome the barriers of patient's health record. That is the main issue with this accessing the patient's health record. Now, Government of India as well as the other places, they tie up with the hospitals and the universities, like IIC is also having this tie up. So in this case, they can mutually share the data, because the hospitals, they share the data to the scientists, and scientists can make the models based on machine learning or the AI based methods, and this can be used for testing the new patients and then go back to that. So this is the circular process, as mentioned in the last talk. So they can improve the performance. In this case, finally, they can use it for developing very reliable AI-based methods. Okay, so now this case, to address how to address this issue, so they made this high protein research, right, fairly using the data, discarding the data which are completely not required, rather than occupying a lot of space. And this requires the several bioinformatics sciences in the life sciences and statistics. And if you see the recently COVID, we have more than 17 million sequences, and it is required to analyze this data not only for COVID-19, for the different diseases as well. Okay, so now how we contribute in health science? Yes, our machine learning and AI based methods, they effectively contribute to healthcare. This is the contributions from my lab. So what we did, so we used various aspects like developing databases and developing algorithms, NGS analysis, structure-based drug design, as well as identifying disease-causing mutations, right, in the healthcare. So we contributed on various aspects, and in this talk, mainly I'll focus on disease-causing mutations in proteins, how this can be useful, right, for design the inhibitors or these lead compounds specifically based on mutations. So we all are familiar with the mutations. It is a change of the DNA sequence, nucleotides, or the change of amino acids, and the single amino acid substitution. So it causes they change the structure, or may change the stability, or change the function, and some of them may lead to disease as well. One of the classic examples is sickle cell anemia. So in this case, you can mutate this E2B, it causes this sickle cell anemia. Likewise, you can see a lot of amino acid substitutions in P53, so which is responsible for cancer. So these mutations are called driver mutations or disease-causing mutations. On the other hand, there are several mutations which are normal, which are not harmful, and these are called the benign mutations or the passenger mutations. Now the question is, you have a given sequence, if any specific mutation happens in the sequence, right, is it possible to predict whether this is disease causing or it is benign mutation? Yes, we develop various methods and it is possible to do it. Okay, due to this advancement of this AI, so there are several research themes to address this AI. Some of the examples, or you can see this the EGFR, there are some mutations, they are in green or benign mutations, and the red are disease mutations. The question is, can we distinguish between these type of mutations? And here this skin cancer, this is the benign and this is for the malignant. So they used image processing and they showed that AI can predict this benign and the malignant close to this performance of this dermatologist. So this is what they have reported in this Nature paper. And here is another Nature paper. So they used various targets like AMC, lactamase, or CS kinase, or BCL2, or EGFR. They scanned millions of compounds and they tried to identify the compounds which are the potential inhibitors, but that agrees well with these experiments. They used various 170 million compounds and they found the potential inhibitors for these specific targets. This AlphaFold database, due to the advancement of AI, so they developed the method and they created databases with more than 200 million structures which can be useful for developing various methods. Fine. So now how to do that? So we need to have a systematic approach to design any specific algorithm and to validate any specific algorithm. So for developing any algorithm, if you see the AI or if you see this machine learning, this is mainly a database driven approach. Right? Physics based approaches, they don't require the data, so they can develop from the beginning. But these bioinformatics based approaches, they require the data. So it is a data driven approach. So developing a data set is very important, and most of your prediction performance relies based on these data sets. If you look into these AlphaFold results, right, if you solve the structures, central part, the core of the region, you can see the blue color one, and mainly at the side, N-terminal and C-terminal, so you can see that they showed with orange color, red color. That means these are predicted with less confident. That means the data which they try to train from this PDB, they are not sufficient to predict these N-terminal and C-terminals. That is the reason that they are less confident. So it is required to have sufficient data sets and the non-redundant data sets to develop any reliable algorithm. Second aspect is, so we need the features. What features are important for predicting this stability or affinity or any of your problem? Last talk we discussed about EGG. So they also use specific parameters which can be used to develop these AI-based methods. So once we have the data and the features, then we can connect based on different methods. Here we use either statistical methods or use machine learning techniques, or you can use AI-based methods to connect these features as well as the data sets. And if you see the machine learning, it requires these features, but AI, if you give the label data, it itself captures the main information from the data and try to predict the model. The disadvantage is the explainability of this AI. So AI can use any of the data and then try to improve the performance, but with the lack of this explainability. The machine learning or the statistical methods, the performance is comparable to this AI, but also able to explain, right, the features which are important for any specific problem. And once we have the method, then we try to assess the performance of the method using various assessment procedures. And then also you need to be very cautious about the overfitting of data, and you have to validate the data using different types of cross validations, right? Once you are happy with the validation, then you can compare with the existing methods or directly apply to the new patients. And if you are fine, then you can make a server, so that will be useful for the application to the scientific community. So this is an approach when you develop any of these your prediction tools on any aspects. Okay. So I'll explain you a few aspects and I go through these applications. First, we need a data. So data set is very important. So to construct a reliable data set, we need to collect the data. Most of the data are available in literature, which are scarcely available. So we need to collect the data and make different databases. So this talk, I mainly focus on the diseases. So we developed various databases. One is the HUAR base, that is the human variant database, which includes the different mutations, both gene level mutation and protein level mutation. And what will happen if you mutate this particular residue? Then which type of the changes in the protein wise or the gene wise, or what are the neighboring residues, and whether this is a benign mutation or this is a disease causing mutation. So how we get that? So we collected the data available in the existing resources, plus we collected data from the literature, because many data which are available in literature are not included in other databases. And the second aspect is we like to integrate with the various sequence and structure based parameters, so that the disease mutation are connected or linked with the sequence and structure based parameters, and that will be easy to relate these features to disease causing mutations. Yeah, so now this has the different search options. We developed the server, so you can see this website, and based on your search option, we will get the data, and from this data you can develop different methods, try to identify these disease causing mutations. And due to the importance of these membrane proteins, because these are the major drug targets, right, in the pharmaceutical companies, so we try to develop a specific database for membrane proteins. So here what we focused in this database is we can see the various information related to the membrane proteins, specifically the topology of the membrane proteins. That means which residues are located inside the membrane, which residues on the extracellular membrane, whether the mutants are in the membrane or outside the membrane, and how they are connected with each other. We found some sort of network based features, and the disease classes, number of transmembrane segments, and so on. So we put all this information in the database, and we developed the server so that it can be searched using your users options, and we can download the data, and this data can be used for developing methods for predicting these disease causing mutations. Okay, this is our front end, and we have the various options to collect the data, and we have these display options so that based on the requirement of the users, they can download the data, and you can use it for this understanding these features or developing methods for identifying these disease causing mutations. Okay. So during the COVID-19, so at that time we try to see the neutralizing antibodies, right? So we developed this UpCove database, right? So in this case we try to collect the data from the literature mainly based on these KD values or IC50 values or EC50 values, right? So based on the different antibodies with respect to the spike protein. So we have the data. So this is your heavy chain, this is your light chain sequence, and we have this data for the different therapeutic antibodies. The next case is in the epitopes. If you find the regions, there is a short peptides which can interact, right? So what will happen if you mutate? So either at the antibody level or at this protein level. So here we try to predict the mutation effects on the affinity between the antibodies as well as spike protein, as well as the stability change upon mutation. So we calculated the numbers and we put everything in our database that is called UpCove database. Recently we developed this database for the carbohydrate binding proteins, right? So here we constructed the dataset for all the disease mutations, in the carbohydrate binding proteins, and you can collect the data whether these mutations are the interface or in the other places of these proteins, and how this affected with respect to mutations. Okay, so now we have the data on various aspects for globular proteins, membrane proteins, specific types of the complexes, and this as well as COVID-19. But now we can derive parameters. So if you know this one, you can derive parameters. This database is mainly specifically for the cancer, that is the cosmic and the TCGA. So in the features, as I discussed earlier, depending upon the problem, right, we can choose the features. For the case of these disease causing mutations, we try to relate the sequence based features, structure based features, and network based features. So we use these physical properties like physical, chemical, energetic, and conformational properties. If you mutate a particular residue, how it changes the property, that's delta P. This given as mutant minus wild type. So you get the difference, that will give you the change in property values. These change in property values are related to whether it is disease causing or it is neutral. Then we have some specific motifs. For example, if arginine is a cylinder residue, so if you take the VRC, so how many times this VRC pattern you can see in disease causing, how many times the same pattern is observed in the case of neutral mutations. From that, we can calculate the odds ratio that will tell you the tendency of any specific motif, right, which is present in the case of disease or neutral. That is what currently they are doing in the LLMs, mainly the large language models, to see whether we can identify this type of mutations or not, right. So we can use it with respect to different type of peptides, tripeptides or pentapeptides, and with some specific wildcard or not. So we can get various motifs. This can also be used to identify this type of disease causing mutations. Making life easy. So also many students are not familiar with the computer programming. So we developed a server that is called the sequence tree feature. In this case, just if you input the sequence, it will automatically calculate more than 200 features, and that can be used for the predictions, right. So we did for the DNA side. As for the protein side, we calculate various features, and if you input your sequence here and your mutation here, you will get the results. Okay, so it is very easy. So if you give the sequence, it will calculate all the features, right, using our method, right. Fine. This is for the DNA based features. Okay, so you can give the DNA sequence here, and you get the values, and you can get these different nucleic acid based parameters. Then the second option is you can have the structures. So there are various parameters you can also derive from structures, because earlier it was very difficult to get the structures from the sequence. Now due to this AlphaFold as well as this hybrid ITSR, now you can easily get the structure from the sequence. So if you have the structures, then we can calculate various parameters such as the accessible surface area or the hydrogen bonds, contacts, and so on. So here we developed another program called the PDB param. Right. So this is an online resource for structural parameters for proteins. So if we give your structures or PDB ID, automatically it will calculate various structure based parameters, and you can use all these structural based parameters as well, right, for developing your machine learning or AI based algorithms. So that's fine. So for example, one example, so we put the physicochemical properties, so we give the various properties here and give the results. So it automatically you can get that. Now you have this data and you have these features. You can connect using either you can use the statistical methods, or you can use the machine learning techniques. There are many machine learning techniques. As you see, there is neural networks or support vector machines that were discussed in the previous talk, and we have these deep learning based methods with various hidden layers, and we can use these methods to predict any of these disease causing mutations. Okay, so you can assess the performance either based on the MAE or the correlation, or you can use this sensitivity, specificity, accuracy, as well as precision recall and AUC curve and so on. That will tell you whether your method is capable of identifying your positive mutations or excluding the negative ones, or there is a balance between your sensitivity as well as the specificity. Right. So you have to be cautious about overfitting of data, right, because your features should be at least how many minutes more? Okay, under 5 minutes I will finish it up. Yeah. Right. So now you can evaluate your performance, right, based on your training and test set or different types of cross validations to see whether your performance is good or not. I go to these some examples very quickly. I'll go through that. So if you go to this EGFR, so you can see there are some mutations which are red in that is a disease, and the green in the case of the neutral. So we used various machine learning techniques. So this can easily predict with an accuracy of close to 80%. And we screened these mutations in EGFR because there are totally 23,800 mutations, and we identified some mutations. That is what currently we are working on doing experiments to see whether how far these mutations are effective. And the second one, for the case of this brain cancer, so we found some mutations are causing this cancer. So we used various parameters, and some of the motifs are very prevalent in the case of these disease causing mutations, and we use this information to predict these disease causing mutations, and we could get the performance with the accuracy of close to 82% by discriminating the disease causing and the neutral mutations. We did it for these membrane proteins. We did it lack of time, I reduced it. We identified the mutations which are in the membrane region, or which are in the extracellular region, or which are in the intracellular region, and we developed models to predict these disease causing mutations, and we could get with an accuracy of close to 82%. And so it works for the different disease classes, different types of mutations and transmembrane segments and so on. Right, so this I keep. Okay, so the case of this structure based drug design, so we used BCL2 as our target. We use QSR based methods to identify some of these new compounds, and we found that there are new compounds. We did the docking and simulations. Okay, these are the compounds we identified. So we did the binding studies. So you can see this is the nanomolar range, and we did the animal studies. So you can see these compounds reduce this tumor level in the case of this is our compound compared to this SM2216. Okay, this is currently we are doing with this collecting of the patient data. So we have the coordination with the Adair Cancer Institute. So they give the data for this gastric cancer, and we are trying to understand the mutations and how this Indian population, these mutants are different from the cosmic database, that is from the Western population. They are very specific because you can see only 33 are common, 247 variants which are very specific to Indian patients. So currently we are working on that to identifying these pathways and the networks and so on. I think I will stop here because due to lack of time. So we discussed about various databases for the different diseases, And from this database, we derive various features and developed methods to identify these cancer-causing mutations with respect to these membrane proteins as well as other proteins as well. This is my team. I thank my collaborators, my students, and the funding from DST, DBT, and IIT Madras, and for their support. And these are my books. If you are interested, you can refer my books. It has all the information regarding these specific mutations. And we are organizing a workshop, that is VECA, Machine Learning for Healthcare. This is a 4th workshop because already we have good response for the 3 workshops. So if you are interested, just you can apply. Deadline is July 27th, and the meeting is 10 hours extensive hands-on. That's a 9th and 10th online. If you are interested, I encourage you to apply, and then you can get familiar with this, how machine learning or AI can be used in healthcare. Thanks for kind attention, and if you have any questions, I'm happy to take.
All the more cheers for Professor Michael and his likes, because they have made life of we doctors so easy by giving us bioinformatics, the machines, the tools for diagnostics and treatment. I'm sure it must be involving a lot of brain work, because collecting data and then pooling it, but you are making our life easy. Only thing I want to comment is, it seems akin, artificial intelligence seems akin to astrology, because you are predicting so many things by this.
But we need to do the experiments also.
Yeah, you need to do. And only the other comment I would say, you in the initial slides said something about COVID, repurposing of the drugs. Did it really help, this artificial intelligence in repurposing, and how?
Drugs available in the literature. So in this case, you can easily see which one you can use it.
So it
in
was
the case
more
of, yeah, because there are many antibodies available in the literature. Some of them are therapeutic antibodies. So these therapeutic antibodies, you can see how they are fit in with respect to your spike, and they can design these antibodies. For that case, you can use this AI to design what are the specific antibodies which can be fit for this specific protein.
I got interested in this bit because I am a virologist by profession, and I could see that there is, in the initial days, it was nothing like that. It was only common sense and ideas.
Yeah.
And now we can generate some data from them.
Yeah, also the mutation effects we can study, because how the efficacy improves with respect to different mutations, because they interact only some specific regions, that is epitopes and paratopes. So here you can systematically mutate and then see how far the efficacy improves based on these specific mutations, and you can design. So then you can go with that antibodies. That is also another approach they are doing.
Thank you very much again for making our lives simpler.
Thank you.
I'll pass.
Sir, thank you for the very insightful presentation, because I'm a pharmacologist, and in the era of reverse pharmacology, this is like a magic, a boon. So we would look forward to any future collaboration if that's possible, sir.
Yeah.
And particularly because I'm working in the area of TB. So we would like future
Actually we do that collaboration with the hospitals, because when they give the data, then we can build construct models.
Absolutely.
And then we can go back and forth so that you can improve it. Yeah.
And moreover, because we have so many MDR TB cases nowadays, so this can really help us.
Yeah.
Thank you so much.
So that was really brilliant, and I have to say that a lot of it went over my head actually. There's one question that I just wanted to know, that in all these models you create, what's your predicate? I mean, how do you compare with and say that's the gold standard against which I compare? Because everything is a new idea.
Yeah, actually it depends on different aspects. One is the reliability of data. If the data set is very good, then we can increase the performance to high level. And the second one is the number of data. If you have more number of data, then we can train very better models for this one. And the third one is we keep some data completely blind. So think that it will come in future. So then when we develop our model with respect to our intuition or AI or whatever, and then we use that one to see whether this model is able to predict or not. If they are not able to predict, then we need to refine our model and see what are the other parameters which are important in these things. If it is fine, then we can see that our model is reliable even for the future cases. Yeah.
Thank you, sir.
Thank you.
Thank you, sir, for your valuable insights.
Thank you.
I request Dr. Deepti Nair ma'am to please felicitate Dr. M. Michael. Sir. I request Dr. Rinku Garg ma'am to kindly felicitate Dr. Deepti Nair ma'am. I request Dr. Priyanka ma'am to please felicitate Dr. Dalip sir. I request Dr. Pooja ma'am to kindly felicitate Dr. Shoma ma'am. For the next session, I request Dr. Pooja ma'am to kindly take over the mic, please.
Very good morning, everyone. It's my pleasure to introduce myself. I am Dr. Pooja Agrawal, Assistant Professor, Department of Physiology, SMSR, and I'm here to continue with the next session of our conference. To chair our next session, I would like to invite Dr. Ratna Sharma ma'am, Professor and Head, AIIMS, New Delhi. Dr. Shalini Srivastav ma'am, Professor and Head, Community Medicine, SMSR. Dr. Devendra Kumar sir, Professor and Head, Respiratory Medicine, SMSR. I would like to invite our speaker, Dr. Madhavan and Dr. Kaushik Mukhopadhyay, on stage to deliver their introductory talk on protocol to publication, use of AI tool in medical writing and research. Dr. Madhavan is an associate professor, Department of Physiology, AIIMS Kalyani. He is co-chairperson of IT sections of AIIMS Kalyani. He is interested in technology updates and is actively developing specialized prompts for large language models that are customized for faculty across various medical departments, helping clinicians leverage artificial intelligence to deliver their most frequently encountered challenges. He is multi-centric coordinator of AIIMS Kalyani for the DST CSRI projects for development of AI-based infant cry analyzer. He leads the project in assessing sleep quality using variable device which uses machine learning algorithms for deriving sleep architecture. Dr. Kaushik Mukhopadhyay is an associate professor, Department of Pharmacology, AIIMS Kalyani, West Bengal. He is MD Pharmacology from Kolkata and has done PGP Artificial Intelligence and Machine Learning from IIT Bangalore and MSc in Artificial Intelligence and Machine Learning from LIMU. His research interests include clinical trials, biostatistics, and artificial intelligence in healthcare. He has 32 publications in Index Journal and is principal investigator for intramural and extramural projects. I request Dr. Madhavan and Dr. Kaushik to deliver their talk. Welcome, sir.
Good morning, everyone. So, thanks to the organizers and Dr. Supriya ma'am for giving us this opportunity to conduct a workshop in this prestigious institute. So, before I get to the topic, I'll get the crowd going a bit. With first disclaimer that we are conducting a workshop where we'll show usage of different LLMs and AI models to, like, from the stage of protocol formation to the publication, what would be involved. We'll be taking you through the process through curated hands-on exercises. Now, coming to this event, right from the morning, all the talks I heard is hardcore ML, machine learning. We are on the other extreme. We are talking about a sophisticated end-user available large language model, and we are just putting you through probably an exposure and training process of the same. So I had a feeling like the first few talks are like art house movies, and we are like bringing a very commercial product of showing the audience how to do a end user product, right? So we felt a little scared about it. And then came the bomb when, yeah. And came the second thing, which is, thanks to Kaushik, he's in pharmacology, but I am in physiology. And I just gave an interview from my promotion 1 week back in front of the same chairperson over here. So I thought, like, you made me more nervous by coming back the following week and giving a talk in front of her. Right. Keeping the jokes apart, I had this slide because it's very nostalgic. So this was a 2000 or 2002 starrer Steven Spielberg movie with the same title, Artificial Intelligence. I absolutely discarded this movie, never made an attempt to watch it, because I thought all Hollywood movies are all about showing some technology which is like out of the world and Americans always saving the world kind of stuff, and I was least interested in this kind. 6-7 years later, I had an opportunity to watch this movie when I was in my undergraduation, and I was just sharing the same thing with Dr. Kaushik. This movie made me cry for 2 hours after I watched the movie. You want to know why? You can check that out yourself, maybe after some time. It's still available on OTT streaming platform. So this movie talks about humanoid robots which are artificially intelligent, and they can be your family, your friend, your children, and so on and so forth. How they give a high fidelity mannequin based artificial intelligence used experience, right? And this movie was so well thought that there is a scenario where there is a character called Dr. No in this movie which can answer every question. You have to pay $10 and you can ask 3 questions to it, and it only gives 3 opportunity. And that was a very early exposure to the idea of prompt engineering. If you don't frame your questions well, you will lose an opportunity to get the right kind of information from the fictitious character called Dr. No. So the humanoid robot here, the David, the character, misses the first 2 attempts by not phrasing the prompt in a right way, and then finally he phrases it right to just find where his mother is. So that's the context. So I think it was a very, very way ahead movie, and nobody in 2002 would be realizing that 23 years later, this would be a household thing, that you have an AI, you have an app in the phone, you pick it up, you key in whatever prompts you need, and it'll give you the output that you want. Not only confined to our field of interest, it's got a wider field of interest, isn't it? And again, I'm sorry I'm having a second movie poster. It's just only introduction, right? I'll take you through everything in the workshop that we have in the afternoon. This one is a biopic on Alan Turing. We all know about he decoded the crypt of Nazis to gain advantage to the British. So one of the earlier experiment of Alan Turing called the Turing test, where a subject interacts with 2 models. One on the other end is humans, and the other on the other end is a text-coded replies by the machine. If the subject is not able to find out who's who, and both appeared same, probably the program has passed the Turing test. So again, this was as early as 1940s. And we are not aware that we have been exposed to AI even before the AI boom has happened, because we have been doing IVR-based calls for quite some time. We have been used Google Maps and even the Google search per se, which has a predictive model. You type the first word, then what does it say next? So all that we have been using, but now we have reached a very, very sophisticated form. So to give an example, it's not only confined to memory retrieval. where there are databases and you can just key in your word and you get the data, I mean the information out of it. Rather, you can make the model think for you, analyze for you, and get the output in the way you want, provided you know how to get the information through a perfectly stringed, proper prompt. In the context, the prompt engineering becomes more important. So we are having a hands-on session on writing good prompts. We are having hands-on session on using different search engines, including the likes of Research Rabbit. And we are also having hands-on session on using analyzing tools like Elicit, which can give almost a systemic review of what you want to get. And we are also giving group tasks on how you can come with your ideas, execute it, and we'll just be there around taking you through the process. Last but not the least, there are many of my friends who are working on music and video generative AIs and photographs. There also a deeper algorithm is involved. And what this all enables is you have a skill set A, but you always wanted to try a B, which involves a completely new skill set. Now AI breaks the barrier that if you know some basic of it, you can also do B. Now, is it dangerous? For us, maybe I'll put it like this. Your patient can have the lab report screened by AI, almost have an idea, and probably he's coming for confirmation to you when he walks into your clinic. So it just makes us to be more responsible, more aware, but vice versa is also true. When a civil engineer gives you a plan for a building, you just don't simply buy it, you do a deep research learning on it, and then you find out what is happening. So then one last experience I wanted to share is we went with this idea of teaching the audience on how to use large language models. We did one workshop in Chennai, we did one workshop in Kolkata Medical College, we did it in-house in our institute in AIIMS Kalyani as well. And what we realized was, it was a mixed bag of senior professors to young residents. Whenever we gave a complex task and made it very simplified, the crowd was very happy. But at the same time, when we showed them that it takes 5 minutes to prepare a 2-hour lecture with AI, they were so disappointed. It just felt like, oh, you are making fun of my whole life experience. I used to sit every day and prepare slides for around 20 days, and then I used to do these adjustment for making a flow chart, this triangles, box, rectangles. I used to sit and draw myself in computer. Now you do it in 30 seconds. How is it even fair? Now the same thing came across every industry. Whenever the skill set that is required of the industry was made simple by AI, people were very upset. Now, is AI a threat to skilled labor? If you ask that question, the answer is, when computer came, it was a threat for many skill. But now we have embraced computer. AI has come, it is a threat for many skills that is existent, but I think the new skill set going forward is how to use AI, and probably we are here to empower in the process. So see you in the workshop in the afternoon. And the first part of the workshop, which is the evolution of various AI models, will be taken forward by my colleague, Dr. Kaushik. Thank you.
Hello, good morning. So basically the purpose of this session is to give you a kind of trailer of what is going to happen in the workshop. So Dr. Madhavan has already introduced the concept of AI in a broader term. So I will be a little bit dig deeper to that. So we prepare ourselves to be more technical in a way. So if you see the term artificial intelligence, it is actually an umbrella kind of term, or I will say it is a PowerPoint term. Like if you see a little bit technical, you will see the term like machine learning, and even the subset of machine learning and deep learning. So what is the difference? I think many of you are thinking it is absolute synonymous. Actually, you can say machine learning is a subset of AI. AI, like suppose if you have an auto AC in your car, which automatically adjusts itself temperature and humidity based on whatever the outside temperature is. So it is a rule-based formula, like, and like suppose if I buy an AC and someone else also buy an AC, in the same weather, it should behave like in a similar manner. But now suppose if you have AC which can learn from your behavior, like I am a person, suppose I want a little bit cooler temperature. So whenever it sets in 24, I reset it in 22 degrees Celsius. And someone else who likes little bit warmer, he shifts the temperature to 26 degree. So after 1 month, if my AC, whenever I switch on, if it fixes temperature near my choice, 22 degree, and if your AC, it is fixing towards 26 degree, that means it has machine learning in it. So the idea is that more and more it is exposed to the data, where the data is coming from, we are giving it. We are giving the data to Google, Amazon, Netflix, to everyone at every seconds. You are carrying mobile and giving a lot of data every seconds to the companies. So we are telling them this what we like, where we go, and based on that they are curating this, they are selling this data to the advertisement, the companies, so that they can curate the advertisement. They will show me the mobile or gadgets, they can show someone some say dress or something like that. So everything is happening with AI, and in a more technical term, it is machine learning, and one subset of that is neural network. I think you were listening to Madam's lecture, so she was like telling about SVM, support vector machine, or random forest. So you can consider these algorithms as a machine learning algorithm, but the neural network part as a deep learning algorithm. And this actually, like what AI is doing now in healthcare, like it can do drug discovery, it can do diagnosis, it can do prognosis, it can actually understand the data from very, very large big data set. So I will not spend any time on this. Later I will move forward to, like, nowadays if you ask like anyone almost who is little bit oriented with current scenarios what is happening, they will also tell you AI. So basically with the AI, what they mean is actually generative AI, the ChatGPT boom you can tell about. So basically it is generative AI. So again, it is a subset of deep learning, you can say. And the specialty of this is that it kind of advanced autocomplete. Like Madam was preparing something where you think and the arm will move. Here you will think and you will type a bit, it will now extend your thinking. Suppose I want to write a protocol on, say, in a drug in rheumatoid arthritis, how it works, or something like that. I want to write a review of literature. So it can give a framework. From there I can start working on. So something like that, very advanced autocomplete. And so what is, again, little bit technical of generative AI, we can call it large language models. How this is happening, how this autocomplete is happening? Because of, they have made models which is very large and it knows language. It's a very simple way. So if you ask something, it will try to predict the next word. All this AI, the main purpose is to predict. Like the previous speaker was telling, like he wants to predict what will bind in what protein structure. So similarly, there are so many models you can make which will predict disease of a person, whether he has or not, will the person die or not with COVID, something like that. Here we are trying to predict the next word. So I'll just give you a simple task. Can you predict the next word? Yes. Can you predict the next word? Yeah, you can be, but it will be grammatically incorrect. So, is. Now, next word? Gukesh. Yeah? So how did you do it? So basically, as soon as you see current chess world, immediately, based on your whatever language you know till now, you have predicted that the next word must be champion. And this is the basic of this fill in the blanks, what we torture our kids with. So, so the same way, LLM is also working. So LLM has been fitted lots and lots of data. Okay. So it has numbers, it has punctuation marks, it has, of course, the words also. So what it is trying to say is predict the next word. So Paris is a city in, so now it will give weightage to France and the Logan, whatever, like it may be Captain America, it may be Narendra Modi. Based on that, it feels that France should be the appropriate word. So it will take France. Okay, it may be Europe also, but it feels that France is the most appropriate word. So the next word it will predict. So I think you have, whoever has used ChatGPT or something like that, you will see that the whole thing will not come at once. It will come one by one. Why? Because the whole thing is not there. It is predicting the next word. As it is filling up the blanks, it is going to predict the next word, so the next word, so the next word, so it will come in. So if you see the little bit history of it, so actually the idea came long back from Alan Turing, Dr. Madhavan has already said, But in a form of chatbot, actually it came around 1967. It is a kind of psychological chatbot. It is a very primitive one, but it worked little bit. But then gradually we have more and more computational powers. Actually the neural network part was done by Rosenblatt. Like he was a psychologist. So the idea of neuron came from there. That how neuron works, it also, he applied it into the mathematics, and ultimately it becomes artificial neural network, now deep learning, now it is totally large language model. And actually the revolution happened with this 2007. You can see Google transformer architecture. So this is the architecture, this is the paper which started that boom, that all attention is all you need. Very nice name also. So from this paper, everything started. Attention, where the attention is, that what is the context. Based on that, is it a Paris? So based on that context, I will make the prediction that it should be France. So something like that. So from there they started the work, it is 2017. And now it has now it is 2025, ChatGPT 3.5 came. The GPT 3.5 actually, then the other models we have, Claude and all these things. So in our workshop, we will try to demonstrate how you can use it for your own day-to-day work. Like it is not something that someday it will be effective. So basically, what we hope that the AI which is available here and now, how we can apply it for our purpose. So why should we use the AI tool? Now, usually we start with blank page. So basically we can think that we start from average. What AI can do, they will give a framework so that you can work on that. So you start at good level. So now you have to make it great, and you can go to outstanding level. But you have to put the same amount, okay. Suppose you thought that you will put 5 hours for a review article, say review of literature. Ideally with AI also you should put around 4 or 5 hours. Then you will get the outstanding level. So with that, so basically we can work faster, very fast we can work. We can go through the literature very fast. If we are not understanding something, we can simply ask it, I am not understanding it fast. So you can understand fast and work again faster. And sometimes the work is very boring. Suppose you have done all these things, but in your paper, okay, as writing. Many of us actually writing. But what if you have to transport that into an Excel? Transform that into an Excel. It is a boring word, right? Because you have already prepared it. Now you have to type it. Boring word. You can take a picture, you ask to ChatGPT that you make a table. Of course, it can make some mistakes, but you just fix the mistake. So the boring word becomes very fast and you can do it. But of course, this figure is very important. So now you can think that you are standing and you are there in the 6 feet level. Now you have a help of an AI, which is a stool here. But if you think that I will spend what I can do in 5 hours, now I will spend only 1 hour, and the rest of the 4 hours I will just spend in movies or something. Of course you can do it, but if you stay in the 6 feet level, then nothing will be achieved. You are on the same level almost. So what I will request that you use AI and use the same amount of brain. Then only you can reach the higher level, that is the 8 feet high. And from 8 feet we can go to 10 feet and the sky is the limit. So that should be the way. But is it everything good? Of course not. There is a problem, lots of problem. One of the major problem is hallucination. As it is predicting the next word, it will predict anything. Irrespective of it knows, it doesn't know. So it will predict something because it has to give a weightage to some words. So there is the problem of hallucination. Even if it does not work, I think you have, whoever is using ChatGPT, they give some peculiar kind of reply sometimes. So why it is happening? Because of the hallucination. So that is the thing we will take you to the workshop also, how to deal with this. Just I am giving you a glimpse of how we can deal with it. We can do fine tuning, which is a very costly method. We will not do it. But what we can do, we use RAG, that is, we can upload a PDF or something like that, and we will tell only you find from this article. Suppose I want to make something on heart failure, I will take a part of Harrison, I can take a part of, say, our three-party pharmacology and relevant parts. I will upload those documents and then I will tell make a gist or make a summary from this only. So then the chances of making mistakes will be lowered. So this is a RAG technique. And of course, prompt engineering is very, very important. Like if I ask you where do you live, you may say Delhi or Noida, or I will say Kalyani. But if I ask you that tell me your address so that I can send something by Amazon, of course, you will give much more detail. So that is how the prompt engineering works. The same way you talk with a person based on what you need, you have to tell it more, and you have to tell more contextual, and you can get the answer you need. And it is not a one-day process. Actually, I feel a person takes at least 5 or more years to learn Google search, actual Google search if you feel. So the same thing applies to here also. The more you talk with it, the more you will learn how to deal with it. And of course, human oversight is most important. Whatever it gives back to you, do not believe by its face. You should check everything. And that's why our cognitive part should always prevail. And the free tools are there, but I will recommend that probably you will understand after the workshop we do that probably one subscription will be better. But still, it is up to you, of course. So in the workshop, we will see you. We will deal with prompt engineering, and we will deal with specialized tools to safeguard you from the problems of hallucination, and see you there. Hopefully, you will enjoy the session. Thank you.
Any questions, chairpersons?
Okay. Dr. Kaushik, thanks, and Dr. Madhavan, thanks for this introduction. I think 2 important things are ask the right questions. That is, I think, the most important. And second, he has kind of warned the first 2 rows senior people, you need to accept what they are going to say. I mean, the thing that you said, you take 1 hour to do something, now it will be done in 30 seconds. So we will have to change our mindset to accept what they are going to show. That is more important. Thank you very much.
Well, thank you for this. Actually, I want to give you an analogy. When first time the photography came, people thought that this is not an art. Okay, actual drawing is the art. But now you can see where is the photography. So the same thing will happen with AI also. Like everyone will use AI, and ultimately that will be the usual thing. Thank you.
Thank you, sir, for sharing your knowledge with us. It will be a great pleasure for us to listen to you again in your future events. I request Dr. Ratna Sharma ma'am to felicitate Dr. Madhavan. Thank you, sir. Dr. Devinder to felicitate Dr. Kaushik. I request Dr. Supriya ma'am to kindly felicitate Dr. Ratna ma'am. I request Dr. Shalini Rastogi ma'am to felicitate Dr. Shalini Srivastava ma'am. I request Dr. Manish sir to felicitate Dr. Devinder. Thank you everyone. To chair our next session, I would like to invite Dr. Shobita ma'am, Professor, Department of Physiology, SMSR, Dr. Saifa M. Latif ma'am, Associate Professor, Emergency Medicine, SMSR. I would like to invite our speaker, Dr. Ronita Jeena Chandran, Ms. Vinila Rebecca Jacob, Ms. Aswati T to give introductory talk on the topic of their workshop, MedSim, Computer-Based Medical Simulations, Online Skill Lab and Virtual Patient Cases. Dr. Ronita Jeena Chandran is a Senior Project Manager, Amrita Create, Amrita Vishwa Vidyapeethan, Kerala. Her extensive portfolio includes USAID supported projects in collaboration with Johns Hopkins Program for International Education in Gynecology and Obstetrics, focusing on clinical care for healthcare practitioners. This project has been adapted into CME for nurses in Goa. She manages innovative projects such as game-based medical platforms that simulate real-life clinical scenarios to enhance clinical skills and critical thinking among healthcare professionals and students. I now request them to come on stage and deliver their talk.
Hello everyone. Welcome to MedSim 2.0. I'm from Amrita University. Actually, we have a workshop in the second half for which both of my colleagues, Ms. Ashwati and Ms. Vinila, will be joining me. So I'll just quickly explain what MedSim is about. And it was developed by Amrita Create in collaboration with AIMS Bhubaneswar and CDAC Trivandrum. It's a MATI funded project, and what's unique about this platform is that it was built for undergraduate medical students, and we are a part of the university, Amrita University. We are a research initiative where we develop different technology-based educational platforms. And in medicine, we have developed about 4 such platforms. I will show you 2, but during the workshop, only Medicine 2.0 will be done. Maybe at a later date, if any of you are interested, we can come back for the second platform. Now, like I said, we are part of Amrita Create, which is the Center for Research in Analytics, Technology and Education. One of our key innovative educational platforms is O-Labs. I don't know if any of you have heard about it. It's actually online labs for school experiments, which was endorsed by NCERT and CBSE. After that, we developed MedSim. Now, this is the first platform I just want to briefly talk about. It's called DISHA, which is the Digital Shiksha for Advanced Clinical Capacity Building. And we collaborated with JAPIGO, which is a Johns Hopkins University affiliate. And it was a part of the RISE project, which was actually a project which developed different modules, educational platforms, etc., which targeted respiratory emergencies, etc. And this was funded by USAID. And basically, this project identified certain gaps during respiratory emergencies such as COVID-19. They found out that different target population, like the nursing community, the paramedical staff, emergency technicians, etc., were not able to cope during COVID-19 pandemic and various other epidemics. And they wanted us to build something which was innovative and which would bridge those gaps. And that is how DISHA came about. So DISHA is not only platform-based cases, we also have virtual reality cases. Only thing is that it's focused on critical care medicine. So these are just some components which are available on DISHA. There are 33 simulation-based cases. Some of them are like based on mechanical ventilator scenarios. Some are based on vaccination scenarios, biomedical waste, such topics. Some are based on oxygen therapy. Like that, we have various learning objectives tailored into each of the clinical case scenarios. And what's interesting is that there are some game-based elements involved in this. Like there's an avatar which will take the user through the clinical scenario. There will be these prompts, and then there are these objectives, like I've mentioned before, which actually help the student or the user identify their gaps, and it gives them instant feedback. At the end, there is a review report. There are analytics, learning analytics also included in this platform. And that all this helps the user to actually learn on the go and also identify the gaps and then try to close those gaps by going through the reports that are made available to the individual as well as the groups who are involved in using this platform. I'll just play a quick 4-minute video. You will see a case list page. Each of the cases have a case summary. You will see an avatar with different prompts and different activities. There's one on mechanical ventilator where the user can actually interact with the ventilator, make different changes in the values. And then you will see the reports page. Then other activities where they can interact during the clinical scenario. So you can just watch this video to get a better idea. I think there's no sound. Is there audio or something? It come?
will give the orientation on will give the orientation on how to use the DSHA platform to enhance your skills in critical care. Each case will have different steps to solve, and at the end you can see the review report. You can practice any number of times till you become perfect in each skill. You can select any case from the list. You can read the complete description about the case before you start. You can refer to case summary, objective, game instructions, reference material and acronyms on the left pane. In this kind of activity, you can roll over to see the details and click on the hotspot to select. You can also deselect by clicking again. In this kind of activity, you can roll over to see the details and click on the hotspot to select. Click confirm to submit your answer. In this kind of activity, you can set the values as required. Click the tab you want to change. Once you are okay, click on confirm. You can see correct ones in green and incorrect ones in red. You can also know the justification by clicking on the question mark symbol in each activity. You can match the relevant by clicking on both ends. You can click on confirm and see the feedback. In some activities, based on visual cues, you need to select an appropriate step. In this type of activity, you can sequence the steps by selecting from each drop-down. For each correct option, you get experience points. In this type of activity, you can follow the sequence by selecting the items. In this type of activity, you can follow the sequence by selecting the items. You can see the correct sequence in the feedback. In this type of activity, you can arrange the steps in sequence by dragging to right place. You can refer the image for a correct sequence. This helps in understanding the sequencing in each phase. You will get to see latest report here. At the end of the case, click OK to see the review report. In the review report, you can see your rating for each learning objective. Here you can choose to replay the case if you want. On top right corner, you can click the icon to view skill report. You can refer to your own skills report here. Based on this, you can work on skills that need intervention. At the end of the case, click OK to see the review report. In the review report, you can see your rating for each learning objective. Here you can choose to replay the case.
So this was the Disha platform. What you saw was on the live platform itself, and as you saw the reports, which helps the users to, better improve themselves. Now I'll just move on. Disha was awarded the first runner-up award for Best Innovation in Healthcare and Hospital Technology. Now we've also done similar platforms in Ayurveda, AyurSim and AyurCell. AyurSim is for, again, undergraduate students in Ayurveda, and AyurCell is for clinical practitioners. And now I'll talk about MedSim. Now, MedSim has clinical cases as well as first and professional subjects or modules. And what makes it unique is it's freely available to everyone who has access to it. So today, maybe in this presentation, I will share some credentials. And in the workshop, we'll have a hands-on session of the clinical cases, the first professional modules, and also we have a few virtual reality cases. So those will be covered during the workshop. But right now in this presentation, I'll give you a brief idea on how to use the platform. So there's quite a lot available on the platform. As you can see, there are about 78 to 80 cases, and we have more than 200 simulations on the platform. I won't be able to cover everything today, but what you see today will help you go back and actually try out the different modules and activities available. We have covered 24 departments in medicine. It is aligned with the NMC curriculum. So in 2013, we started phase 1, which was completed. It was funded by MATI, and that time we had 2 systems covered, that is cardiovascular and respiratory. There were no first and second professional labs back then, because we had to build the platform from scratch. And at that time, there were 10 virtual patient cases, and we got it reviewed by the government, and they had appointed Professor Randeep Guleria, and he had given us some valuable feedback, which we had incorporated in phase 1 itself. And then Dr. Shalini Rajneesh also recommended it to the Directorate of Medical Education in Karnataka. After showing it to different colleges across India, we got a lot of interest from various colleges and national premier institutes, and all of them had one thing to say, that is, you need to include more clinical cases, you need to include first and second professional subjects. That came from the students, because they wanted a platform which would support all the years of MBBS. And some of them had asked us to enhance the treatment module. So the treatment module work is still going on. I will show you a sample of what you can expect. Maybe after a month it will be up and running. And but before that, we have about 60 plus clinical cases and quite a lot of first and second professional modules available on the platform today. So just to give you an idea, these are the departments which are covered in MedSim 2.0. In the end, we'll have 38 simulation labs. As in, for example, biochemistry, the student can actually try out the different experiments. ECG, we have an activity where they can connect the ECG leads and then generate the ECG report. Then anatomy, also we are trying some new simulations in dissection, knee joint, ligament, etc., brachial plexus. All that work is going on. We also have a learning analytics and a question bank module where we have different assessment questions also. So there are 4 different types of modules available on MedSim. One is a theory-based interactive module, which is nothing but first and second professional subjects. We have cases with game-based elements, which is a bit similar to Disha, but not so advanced. Then we have virtual patient clinical cases, which I'll be showing a few of the departments. Then we have virtual reality cases, and we have brought 2 virtual reality devices which you can use to see the cases that we have today. All of these 4 different types are available on MedSim. Now this is the URL medsim.in. This is the home page that you'll get when you type medsim.in. During the workshop, we'll do a hands-on session just to explain the different features available on the platform. There is a menu button, and you can just go through those different features, screenshots, there are some write-ups about the platform, etc. Now just briefly explaining the first type, theory-based interactive modules. When you use the credentials we've given you, you will see a case list page, and then on the top you will see a button called Online Skills Lab. This will give you access to the theory-based simulation modules, and each of these first and second professional subjects are divided into subjects. Each subject is then divided into topics, and the topics are divided into subtopics, and under each subtopic there are some concepts that we provide which the student has to go through. In case there are experiments, there are procedures involved. Then we have some smart review activities or simulations which the student can try out. It will give them better understanding of the concepts that are provided under each of these topics. And finally, there are assessment questions also, and a resource tab which lists out the references which were used to develop the module. This was a requirement from the students because they wanted to know from where we have sourced this content and the smart review activities. This is the second type. This is essentially the emergency medicine cases. There are different types of activities like you saw in Disha, match the following, drag and drop, then management protocol, you know, they have to arrange it in the correct sequence, true or false questions, etc. All this is actually done in such a way that it takes the student through a particular clinical scenario which is guided by the avatar you see on top. So we have a case, and all these different types of activities are incorporated into that case. So they can easily navigate their way through the emergency medicine cases. The third type, this is the virtual patient clinical cases. We have cases from general medicine, general surgery, obstetrics, opthal, ENT, dermatology. Pediatrics is not yet up, but after a month or so, we'll have pediatric cases also. Orthopedic cases are there. And I'll show you a few of them today. This is how we have developed the new treatment module. There is a treatment plan, and it's divided into 3 different sections. They can select the drugs, then if there are any procedures, they can select the procedures, and finally we have lifestyle and support. So that I'll show you during the workshop. Now the fourth type is the virtual reality cases. These are samples of few of the virtual reality clinical cases we have done. We also have different procedures like pleural tap, endotracheal intubation, incision drainage, etc. also done, which we'll show during the workshop because it takes time to wear the device and do it. Now in each of these cases, there's a feedback form in the review section. If there is anything you would like to tell us or let us know, you can just access that feedback form and just fill in the form and give your feedback, which will help us improve MedSim 2.0. So you can save these credentials, the URL medsim.in, and to access it you need a username and password. You can use guest user, and password is guest@2024. Those of you who cannot attend the workshop later on, you can use these credentials and access the website. I hope in the presentation it's clear like how to use it, but I'll just quickly show you. Before I start the live demo, is there any questions or anything anybody has? Yes, yes, yes. Mapped. No, ma'am. What we have done is we have approached those national institutes to give us the topics which are important for their departments. So those we have used, and they have given us the materials, the content and all. So we are assuming the competencies would be, you know, aligned with it. But we Like for example, ma'am, can you give me one? That is there. But that is incorporated in our clinical case. I'll just show you a demo.
Ma'am,
NMC.
Ma'am, I have a basic query. In AI, my understanding says that to create the algorithms, we need thousands and thousands of data. Yes. So, if we are claiming this as a AI model, so where is the source of data from when these products are being launched and used? Where is the source? What is the source of these data?
We have subject matter experts because we are collaborating with AIMS Bhubaneswar. They provide the data to us, whether it's clinical data. It is all we don't know which particular patient or anything, but they give us the data. And similarly, Amrita medical team also gives us the data. So, but what we do is we are the development team. So we add the data at the back end, and then you will see it. I'll just do the demo, ma'am. Then, right now we have scope to add as much cases or modules which are needed because the structure is in place. Okay. So, but then we do need a development team and a medical team to give us the data. So it is not like you use ChatGPT and directly it will give us the data like that. Because it is a targeted approach for students. There is a certain, doctors or the faculty want the student to learn a particular thing. That is the data they give us. So that was what we had proposed to the government, that there are some critical topics that a student has to learn, which is aligned with NMC, and the subject matter experts have given us that. Okay, but in future, we can always add as much data as needed. Okay. Yeah, the remaining things we'll take it during the workshop. I think, yeah, I'll guide you through the hands-on session. I'll unplug. Okay, thank you, everyone.
Is it done? So thank you, ma'am, for the wonderful presentation. Yes.
Thank you, ma'am, for sharing your deep knowledge about medicine with us. So I request Dr. Shobita, ma'am, to kindly felicitate Dr. Ronita, ma'am. Thank you, ma'am. I request Shobita, ma'am, to kindly felicitate Ms. Vinila Rebecca Jacob, ma'am. I request Shobita, ma'am, to kindly felicitate Ms. Aswathi, ma'am. इनॉग्रेशन करेंगे, ठीक है। I request Shobita ma'am to kindly felicitate Dr. Saifa ma'am. I request Shalini ma'am to felicitate Dr. Shobita ma'am. Inauguration है ना?
We'll begin with our inauguration ceremony. Just a few
रघुकुल रीत सदा चली आई, प्राण जाए पर वचन न जाई। तदियाना दीम दिर ताना देरे नोम, तदियाना दीम दिर ताना देरे नोम, तदियाना दीम। रघुवर तेरी राह निहारे, रघुवर तेरी राह निहारे, सातों जन्म से सिया गर मोरे परदेसिया, आओ पधारो पिया गर मोरे परदेसिया, आओ पधारो पिया। दीम ता ना ना दे रे ना, दीम ता ना ना दे रे ना, धनी सा मा सा गा मा दा नी दा मा गा पा गा मा पा सा गा मा पा नी नी गा मा पा नी दा पा मा गा रे गा मा दा पा रे मा पा दा मा पा नी नी दा पा मा पा गा मा रे सा नी सा रे रे मा मा पा पा दा दे मा मा नी 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 रे सा नी दा पा मा पा दा नी दा पा मा गा रे सा नी सा रे रे गा। ना तो मैया की लोरी ना ही फागुन की होरी, मोहे कुछ दूसरा ना भाए रे, जब से नैनाए जाके एक धनुर्धर से लागे, तब से बिरहा मोहे सताए रे। ना तो मैया की नोरी ना ही फागुन की होरी, मोहे कुछ दूसरा ना भाए रे, जब से नैनाए जाके एक धनुर्धर से लागे, तब से बिरहा मोहे सताए रे। दुविधा मेरी सब जग जाने, दुविधा मेरी सब जग जाने, जाने ना निर्मोहिया घर मोरे परदेसिया, आओ पधारो पिया परदेसिया, आओ पधारो पिया। थैंक यू।
Ladies and gentlemen, I, Dr. Rupali Mittal, would now propose to formally inaugurate a conference and workshop by inviting our esteemed dignitaries, Shri Y.K. Gupta Sir, Dr. Gitika Khanna Ma'am, Dr. Ram Murthy Sir, Dr. Nirupma Gupta Ma'am, and Dr. Supriya Gupta Ma'am to kindly light up the inaugural lamp. MBBS students shall render Saraswati Vandana along with the lamp lighting.
Sa sa ri sa ni ni sa ni pa pa ni pa ma pa ga ma pa ni da 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 sa pa 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 ni ma pa ma ga ma pa ni sa.
Ma Saraswati Sharde, Ma Saraswati Sharde, पूर्ण इस अज्ञान उदधि से, पूर्ण इस अज्ञान उदधि से, वीणा पानी तार दे, तार दे, तार दे, माँ सरस्वती शारदे, माँ सरस्वती शारदे. सूर्य ब्रह्म शिव विष्णु गजानन, जिन चरणों को सेवते थे. सूर्य ब्रह्म शिव विष्णु गजानन, जिन चरणों को सेवते. हम शिशु हैं अज्ञानी माता, इन चरणों का प्यार दे. वीणा पानी तार दे, तार दे, तार दे, माँ सरस्वती शारदे, माँ सरस्वती शारदे.
May I now invite all our dignitaries to kindly take their seats on the dais, please. Please put your hands together for Shri Y.K. Gupta Sir, Dr. Gitika Khanna Ma'am, Dr. Ram Murthy Sir, Dr. Nirupma Gupta Ma'am, and Dr. Supriya Gupta Ma'am. It gives me immense pleasure to introduce our chief guest, Dr. Gitika Khanna Ma'am, Principal and Director Professor, Pathology, Vardhaman Medical College. She is an alumnus of Lady Hardinge Medical College, and her areas of research interest are orthopedic pathology, medical education, and mycopathology. She has more than 100 publications and has written 4 textbooks of pathology. She is a life member of Indian Pathologist and Microbiologist, Indian Association of Cytologists, Dermatopathology Society of India, and Indian Musculoskeletal Society. She is a member of Expert Review Committee ICMR. She has more than 30 years of teaching experience. In addition to all her teaching and research experience, she is the principal of Vardhaman Mahavir Medical College for the last 5 years and has taken the college to new heights. She is a completely hands-on, dynamic and dedicated principal who has her best interest of the institution, faculty and students at heart. She has achieved numerous milestones in development of college, which include setting up of skill lab, getting the college building extension, which includes an auditorium, approved reviving MEU, contributing in making the complete Art of State library, etc. She has successfully conducted convocation ceremonies over the years for both undergraduates and postgraduates. I welcome you, ma'am, amidst a big round of applause. I request Shri Y.K. Gupta sir to kindly felicitate our chief guest, Dr. Kritika Khanna ma'am. It is a great honor to have Honorable Vice President, Pro-Chancellor Sharda University and Vice Chairman Sharda Group of Institutions, Shri Y.K. Gupta sir. Sir is a visionary who has plethora of experience behind him and has been a role model for many years. He is leading educational reformer who has given new direction to the teaching methodology practices across the country. Under his stalwart leadership and dedication, Sharda University is today a landmark of excellence in education worldwide. I welcome you, sir, and I request Dean Ma'am, Dr. Nirupma Gupta, to please felicitate our Pro-Chancellor, Mr. Y.K. Gupta, sir. I would now welcome our medical superintendent, Dr. Rammurthy Sharma sir, who is a highly experienced medical professional with a wealth of knowledge in critical care medicine. Currently serving as the professor of anesthesiology and critical care medicine, he brings 34 years of valuable experience from his service with the Armed Forces Medical Services. Dr. Sharma has also served as an examiner for MD, DNB and DM examinations. Additionally, he is a recognized teacher affiliated with Delhi University, MUSH Nashik and RGUHS Bangalore. I welcome you, sir, and I request Dr. Shri Y.K. Gupta sir to kindly felicitate Dr. Rammurthy Mishra. Now I would like to welcome Dr. Nirupma Gupta ma'am, Dean School of Medical Sciences and Research, Sharda University. Ma'am is the alumnus of prestigious Lady Hardinge Medical College, New Delhi. She plays a multifaceted role in the institute, has more than 20 years of teaching experience, is a great administrator and a wonderful mentor to all our 250 graduates admitted every year. She is very enthusiastic and has great connect with both faculty and students. I request Dr. Rammurthy sir to please felicitate our organizing chairperson, Dr. Nirupma Gupta ma'am. I welcome our head of department, Dr. Supriya Gupta ma'am. Ma'am is an alumnus of Lady Hardinge Medical College and has 30 years of teaching experience with major focus on autonomic functions. She has joined our institution about a year back, and her robust personality is a great inspiration to all of us. I request Dr. Ramurthy sir to please felicitate our head of department, Dr. Supriya Gupta ma'am. She is our organizing secretary for the conference and workshop. I request sir to also kindly felicitate our second organizing secretary, Dr. M. Shobhita ma'am. She is professor in Department of Physiology, SMSR. I request sir to also felicitate our joint organizing secretary, Dr. Rupali Mittal, which is me. May I now request Dr. Supriya Gupta ma'am to kindly address the session.
A very good afternoon to all the dignitaries on the stage and to all the delegates who have traveled from far to attend the conference and workshop on artificial intelligence, its application in medical education and clinical practice. As we all know, AI, the pace of development makes this moment very critical. As highlighted by the Stanford AI and Health 2025 conference, AI is moving swiftly from theory into clinical workflows. Our goal over these 2 days of intense academic discussions and hands-on workshops is reshaping how we train our future clinicians and deliver patient care. We have with us here the very best in this field to help us achieve this goal. The conference and workshop has a dual focus, medical education and clinical practice. In the field of ME, that is medical education, we aim to examine AI in digital learning, adaptive tutoring systems, simulation-based training, virtual reality, etc. in teaching. The hands-on sessions will specifically focus on deploying AI in simulations, diagnostics, patient monitoring and integration into teaching methods. They will also focus on the use of AI tools in medical writing from protocol to publication. So with this brief background, let me welcome you all and let's seize this opportunity where we have leaders in the field to guide us and help shape the future of medical education and clinical care. During the learning process, we must ensure that innovation and human values and ethics go hand in hand. We sincerely hope that at the end of this academic bonanza, our delegates go back armed with concrete strategies to embed AI into medical curricula and clinical practice. I once again welcome everyone present here today who have enriched our effort with their impactful presence. Thank you so much.
May I now request our Dean Ma'am, Dr. Nirupama Gupta, to kindly share a few words with us.
Thank you, Rupali. With regards to the chief guests, Dr. Geetika Khanna, Dr. Supriya Gupta, MS Sharda Hospital, the Pro-Chancellor sir has just left, all faculty members, HODs, professors, the well-known speakers here, and dear students. I welcome you all for this amazing national conference which is organized by Dr. Supriya Gupta, the HOD Physiology and her team in association with the Physiologists of India. And the theme taken, that is the artificial intelligence, its role with the medical teaching and the clinical, this thing is the much needed one, ma'am. This was much needed because we have so much of data in the hospital, we had so much of data in our labs. Then we just need someone to actually adequately use that for the benefit of teaching, learning, and for the benefit of the patient care. So this was a much needed conference which has been organized. We have stalwart speakers from IITs, IIMs also. So best AIMS also, AIMS Kalyani, AIMS New Delhi. So I'm really happy to hear this. AIMS Rishikesh also. So I'm happy to hear this. And my best wishes to Dr. Supriya Gupta, HOD Physiology, and her team to take this forward. I want the students to make use of this conference and all the delegates to learn maximum from this. Thank you so much.
May I now request Dean Ma'am to please felicitate our organizing co-chairperson, Dr. Amit Pavaiya sir also. I now request our medical superintendent, Dr. Ramurthy sir, to kindly share a few words with us.
Good afternoon. Honorable Chief Guest, Dr. Geetika Khanna, Dean, SMSR, Dr. Supriya Gupta, invited faculties, delegates, honorable resource person, faculties coming from various renowned institutions of the country, professors, faculty, my dear students. I am very happy that the Department of Physiology has taken up the lead to organize this conference on artificial intelligence in association with the National Association of Physiologists of India. We all know artificial intelligence is a current burning topic. Everybody talks about the artificial intelligence nowadays. It is of equal importance to doctors, engineers, and everybody else. Everybody wants to learn the artificial intelligence. And very rightly said, it's maybe a future of medicine and maybe many other things. It's already transforming the practice of medicine currently, and it will transform the medicine in the future to come, especially in the field of diagnostics, image identification and diagnosis in a big way. Medical research, AI is helping in a big way. And drug discovery. So various fields, artificial intelligence can be used. So I'm happy that we all are here to talk about the artificial intelligence in medicine. In Sharda University, we already couple of projects we are doing, especially we are training our artificial intelligence AI model for the identification of various kind of images, especially the image of endoscopy, image gathered to identify the various kind of disease which we can identify from endoscopy. So I am sure all our young students knows about the much more than many of us. And with this, I would like to say best wishes to each one of you for the learning about the future of medicine. And again, once like to thank the organizers for giving me this chance to be here. And with this, thank you and Jai Hind.
I now request Dr. Geetika Khanna ma'am to please kindly enlighten us with her words.
So, very good afternoon to everyone. I've been very lucky. I found some friends from my alma mater, that is Lady Hardinge Medical College. Madam Dean was 2 years my junior in Lady Hardinge. So, a pleasure to meet you. It gives me immense pleasure to welcome you all to this landmark event which has been organized by the Department of Physiology, SMSR, Sharda University, under the aegis of Association of Physiologists of India. We stand today at the threshold of a transformative era in healthcare, an era where technology, particularly artificial intelligence, is not merely an adjunct, but a driving force, redefining how we learn, how we teach, and how we practice medicine. AI is no longer a futuristic concept. It is here and it is very real. From clinical decision support systems and diagnostic algorithms to virtual anatomic labs and personalized learning platforms, AI is reshaping the very fabric of medical education and clinical care. This conference and workshop were envisioned to be a confluence of ideas, a platform where academia, clinicians, researchers, innovators converge to share insights, to tackle challenges, and to explore the immense potential that AI holds for the future of medicine. We are truly honored to welcome our esteemed speakers, each a pioneer in their respective field. Their presence here reflects the growing relevance and urgency of integrating AI into our medical ecosystems. Their insights will not only educate us, but also challenge us to think in brand new ways. The famous computer scientist Ray Kurzweil once said, "Our technology, our machines are part of humanity. We created them to extend ourselves. AI therefore should not distance us from this wisdom. On the contrary, it should liberate us from the mechanical, allowing us to deepen the human. The goal of AI is not to replace healthcare professionals, but to empower them. AI is a partner that can help us become more efficient, more accurate, and more patient-centric." To our young learners in the audience, you are the future. Let this workshop be your spark. As Einstein once said, imagination is more important than knowledge, for knowledge is limited, whereas imagination can embrace the whole world. I therefore implore you to dream, to question, and to build, both responsibly and boldly. The future of medicine lies not just in molecules and machines, but in minds courageous enough to reimagine what is possible. To conclude, I would like to express my gratitude to the organizing chairperson and the organizing co-chairperson, Pro VC Sir, the organizing committee, especially Dr. Supriya Gupta, who's been a friend, philosopher, and guide for a very long time. We have been in Vardhaman Mahavir Medical College and Safdarjung Hospital since its inception in 2001, and we have been colleagues and friends ever since. So thank you again, and I hope the coming sessions will be equally engaging and equally interesting. Thank you very much.
Thank you, ma'am. With this, we come to an end to our inauguration ceremony. I request our esteemed dignitaries on stage and everybody in the audience to please join us in MEU 5th floor for lunch break. Then we'll be continuing with our workshop. So just a few instructions for the workshop. Group 1 will go to workshop 1 in MEU room 5th floor, the same place where we are having lunch. And then group 2 will go to workshop 2, 6th floor in college council room. Thank you so much. Let's have lunch. Okay, so we'll be meeting there at 2 o'clock for the workshop. Thank you, everyone.